Good morning, good afternoon, and good evening, everyone, and welcome to our workshop, the second international workshop on Dynamic Scene Reconstruction. It's my great pleasure to introduce my co-presenters today. My co-organizers in this workshop, Armin Mustafa from the University of Surrey, Marco Volino from the University of Surrey, Michael Zollhofer from Facebook Reality Labs, Dan Casas from the Universidad Rey Juan Carlos, myself from the University of Bath, and Adrian Hilton from the University of Surrey. Our objectives in this workshop today are to bring together the leading experts in dynamic scene reconstruction, which is a very versatile and expanding field of research. We are aiming to create and maintain a database of datasets and publications with the aim to accelerate the research progress in dynamic scene reconstruction. And so we have started this dataset on our workshop website, and we continue to expand it. We have already a collection there of different datasets focusing on digital humans, but we are always keen to expand this towards other modalities as well, such as general dynamic scenes with trees and general outdoor scenes. So how is this working today? So we're trying out something new. Everything is virtual. The live presentation here happens in Zoom. Most of our presentations today will be live. Only our second keynote will be pre-recorded. The discussions and chat will happen in the Zoom room here. But also, let me move this out of the way. I would like to know you that we are recording these talks. We're actually streaming it live to YouTube, so you can also follow along there. You can use the live chat there to ask your questions. We'll be monitoring that. And later on, after the end of this first run, the recording of this workshop will also be available on YouTube, so you can catch up, watch all the presentations and the discussions and panel discussion at the end. So our program here today is starting right now with a welcome introduction. We'll then hand over to Yaser Sheikh for his keynote. We'll then have a break, about 10 minutes. And in this break, we will continue using the Zoom room for discussion, but we won't be streaming this to YouTube. So please join us in the Zoom room if you would like to chat and have a talk. And then we'll go back to the paper session at 9:35. Again, afterwards, we'll have a short break where we can network and mingle a little bit before our second keynote by Raquel Urtasun. We will then follow this up with a panel discussion, which is between the authors and the speakers, and end with the closing and a best paper award session. So this is essentially the morning session of the Pacific Daylight Time. And in the evening session, the recording on YouTube will be available for you to catch up and watch it. But we will also have a live Q&A session at 23:35 Pacific Daylight Time. So please join us then for half an hour of live Q&A with the authors and the speakers for our viewers in the evening session. So our program today, we have two exciting keynote speakers. The first one is Yaser Sheikh, the director of Facebook Reality Labs in Pittsburgh. He will be talking about metric telepresence. And the second keynote is Raquel Urtasun, the chief ATG scientist at Uber and at the University of Toronto. And she'll be talking about photorealistic simulation with geometry-aware compositing for self-driving. We also have 4 exciting paper presentations in our workshop. You will see what these are about later on. And we're also very proud to announce our sponsor, NVIDIA, has contributed an NVIDIA Titan RTX graphics card. So this is currently the fastest graphics card on the market, a $2,500 graphics card with 24 gigabytes of memory and 130 teraflops of deep learning performance. So the best paper in our workshop will be awarded this prize at the closing session. And without further ado, I will hand over to Michael Zollhofer, who will be introducing our first keynote speaker.
Thanks, Chris, for the nice overview. It's my great pleasure to introduce Yaser Sheikh to all of you. Yaser is the director of Facebook Reality Labs in Pittsburgh, where also I'm working now. He has devoted his work to achieving photorealistic social interactions in augmented and virtual reality. His research is really broad. He mainly focuses on machine perception and rendering of social behavior. And this spans subfields from computer vision to computer graphics and to machine learning now. I'm now very excited for his talk on metric telepresence. Please, Yaser, go ahead.
All right, thank you, Michael. Thank you all for attending, waking up early in the morning or staying up late as is appropriate. I'll share my screen. All right. Are you able to see this? Thumbs up? Yes? All right. Excellent. All right. So we are social animals. This is something which is hopefully obvious to most, if not all of you. And if it isn't, then there is a raft of research in multiple disciplines that tell us that being able to socialize is important for our health, for our happiness, and even for our productivity. And one of the things that's most kind of noteworthy about our sort of need and ability to socialize is how deeply primitive it is, how our perceptual systems, how our cognitive systems, and even how our sort of muscular physiological systems are tuned to social behavior. So for instance, if you take this image, all of you would readily recognize that this is some sort of party, which it is. This is our office party. And over here, you can clearly see Jason is engaged in conversation with Stephen and Gabe over here. But because you and I and all of us understand, how the norms or the protocols of social behavior, you can anticipate that there is a person hidden here behind Gabe. Even though we just see this slight sliver of a silhouette, you're able to guess that people tend to congregate in circles, and he is likely speaking with her. You're able to see that this lady in the background, for whatever reasons, depth perception, her face is in this view, but you know and I know instinctively that she's not part of this conversation in some way, right? It's incredible how much we're able to extract from just this static image. And in reality, scenes are actually flooded with social signals, right? These social signals where people are communicating back and forth. In this particular case, you're able to see that probably James over here on the right of the screen, sorry, not sure if you can see my cursor, on the right of the screen, probably said something, cracked a joke, made an observation, and you can see how, you can see how Dan over here reacted to it, right? He obviously found it humorous, he's smiling, but he's also looking down. And it's kind of interesting to ask, if you were to think about what language you would use to describe what he's doing right now. Smiling and looking down, laughing and looking down. His hands are sort of like a little bit, there's something awkward about it, but it's hard to articulate in language what his reaction is to what James just said. And similarly, if you look at his wife, she's making a gesture. Once again, like it's readily understandable by anyone what this means. The information over there is recognizable to us, but we would struggle to sort of put words to it. And likely the reason for this is that these sort of gestures have either predated language or they have co-evolved with language to provide it the sort of context that's important for us to understand and socialize with one another. But because it is complementary or contextual to language, it's something which is very hard for us to represent. And it's one of the reasons why likely machine vision algorithms, machine learning algorithms have not been developed that can actually estimate or infer these from images or videos or audio data. It's because we don't have a representation to map them to. Like we have language, there's often lots of work trying to translate actions from action recognition from videos and images to language. We don't have this sort of like equivalent representation for this channel of communication that's flooding the scenes we're in. It's what the eminent anthropologist Edward Sapir was referring to when he said, we respond to gestures with an extreme alertness, and one might almost say in accordance with an elaborate and secret code that is written nowhere, known to no one, and understood by all. So machines are entirely blind to this elaborate code, but we are very, very sensitive to it. And it is an integral part of how we socialize with one another. Now, one of the sort of historically, one of the biggest obstacles to socialization is proximity. Proximity determines social relationships. I, as many of you, don't live where I was born or where I grew up, right? And even if you do live where you grew up, you must have had friends and family leave that city or leave that place. And you know, and I know, we all know this truth as well, that when someone leaves a place, the relationships they have with the people in the place they left behind also sort of, you can sustain them for a while, but over time they degrade, right? And so where you live determines who you have relationships with. Who you meet every day determines who you have relationships with. And as a response to this, we've come up with various means to try to overcome distance in trying to establish social relationships. With, for instance, historically, the Postal Service, you could send these messages out asynchronously. They would arrive months or maybe even sometimes years afterwards, but it was a channel of communication that was established over distance, right? Perhaps the next big breakthrough was the telegraph, which instantaneously allowed you to see the other person and what they were. So you could instantly communicate the message that you wanted to across great distances. But it was just the content of that message, and not, in fact, all of that social signal that we were talking about that floods these scenes and enables us to interact with one another. The next step was the telephone, right? Now, this added one layer. It opened that channel towards that extra contextual information, not through gesticulation or facial expressions, but through the tone of your voice, right? But the prosody, the tone with which you said something, not just the raw message, but also that a bit of that contextual information. And not surprisingly, we were so hungry for this. This spread throughout the world. Like, think about the effort it took to establish telephone connections around the world, digging wires, hanging telephone. While folks are being removed, I thought I'd make a point that I wanted to make separately in the talk, which was that these sorts of interactions are so different from real world interactions, right? And this, I think, example is in fact very demonstrative of this. I'm pretty certain the people who had posted those messages or posted those videos, had we been sitting in a room together, they would never have done that, right? And it's because we have sort of established social norms, social interactions. This sort of an interaction would never have happened, or it would be extremely rare or unusual to have happened inside, at least in my experience, attending CVPR since 2000, 20 years now. I have never seen anything like this, right? And it's entirely an artifact of distance constraining how we interact with one another.
So I believe everyone is now removed who isn't a presenter for the workshop.
All right. I will share my screen once again. All right, 1 second. Let me see if I can.
Thank you for your patience, everyone, and thank you, Yaser, for your.
All right. Okay. Are you able to see my screen? Okay, I'll presume so. So as I mentioned, telephone was the next innovation, and it spread throughout the world, despite the pains in doing so. And then the next one, which is what we're all using right now, is video conferencing, right? And this was established in the 50s. I'm showing an iPhone. Obviously, it's not wasn't invented in the 50s, or so we know. But nonetheless, video conferencing allowed us to further open that channel that's contextual around the interaction itself in terms of facial expressions, body gestures, and so on and so forth. And it too has sort of like spread all around the world. And in fact, in this particular case that we're in right now, in this pandemic and our response to it, it's been very clear that the explosion in its use demonstrates how important that sort of contextual information is to all of us. It is in telephone. It is in the telegraph. It is to a large extent messaging as well. Of course, all of these technologies still exist. But it's video conference that's really exploded and enabled us to stay somewhat productive and engaged despite this distance. But what is the limitation of video conferencing? Besides the disruption that we just saw in this talk, that it sort of like depersonalizes interactions in some way, there is this challenge that even when you're video conferencing with people, you can see them, but there is something missing in the interaction. So for instance, in this particular case, Mary, Michael, Salim, and Aaron are interacting, but Mary doesn't know whether Michael is paying attention or Salim is paying attention or Aaron is paying attention. This very element of social interactions, which is eye contact, is missing, right? So she can't tell this. If more people join this conference call, as we have over here, it's impossible to have this sort of like massively tiled screen where you can see anyone. And personally speaking, myself as the speaker, I feel a big difference in speaking in this form as opposed to speaking in front of an audience. Even though I see a sea of small faces, at least I can pick out a few people from the crowd and get a sense of how the audience is reacting, which I cannot do in this kind of a format, right? And then the third reason, which is actually kind of subtle, was in fact noted by Licklider and Taylor in their 1968 paper, which was around this notion of mental models in shared space, right? Perhaps the reason present-day two-way communication falls so short of face-to-face communication is simply that it fails to provide facilities for externalizing models. What did they mean by that? What they meant was that I have a mental model in my head, you have a mental model in your head, and when we're interacting, we use the environment to try to externalize what I have in my mind so that you can get it. We pull out a whiteboard and start drawing on it. You could collaborate with me to draw on it. We take sort of stationery in the room, move it around to start to try to externalize what we're thinking among each other. And this is missing inside VR, inside video conferencing. And now, over the last couple of years, an opportunity has arisen where we might be able to get a step closer to in-person interactions through artificial reality. That's virtual, augmented, and mixed reality, right? With the advent of VR headsets, so obviously they were there for decades ago, but recently commercially viable headsets have formed, like the Oculus Rift, the HTC Vive, Sony PSVR, Google Daydream, and most recently, the Oculus Quest. And these were in VR. Simultaneously, we've seen the Microsoft HoloLens, the Magic Leap, and the new one coming up. And of course, the rumors now of Apple developing glasses as well. Now, in VR or AR, you could actually have a feeling like that person is there with you, or people are there with you in the same space that you're in, right? And it can establish this ability to interact with people. But the core challenge is that we want to enable authentic communication in what is essentially artificial reality. And these two terms, you know, the two key terms in this goal expose the challenge over here, that you want authenticity, like a real feeling of an interaction with somebody else, in what is essentially virtual, augmented, or an artificial reality, right? And what we have to fool is the world's most sophisticated perceptual system, which is humans looking at other humans while they're socially signaling, while they're interacting with them. And we are, as I mentioned earlier, highly tuned. Both our perceptual and cognitive systems are highly tuned for that sort of detail and subtlety, and we extract an incredible amount of information. So we have to somehow enable authenticity in these artificial environments in reality. Now, we've seen there are some social VR apps out there, Allspace VR, Facebook Spaces, VTime, and others. And these usually have these sort of stylized or cartoon avatars. And they're really good for enabling interactions when the interaction itself is not the focus of the session. For instance, over games or something like that. But they have failed to in any real way displace video conferencing as the major means of interaction over distance. As we know, in this pandemic, there's been this explosive rise in the use of Zoom, Skype, and these sorts of apps, but there hasn't been an equivalent explosion of that magnitude in the use of social VR. And so the thesis of our work has been that metric telepresence is sufficient for authentic communication. Now, what do I mean by metric telepresence? By metric, I mean represents true, in other words, metric presence, rather than something that just looks good. So not only should the avatar look like you, it should sound like you, it should move like you, and it should do what you were doing in the real world. In other words, it should attempt to be a proxy for a real interaction to our best ability. And metric in that sense is that's up to a metric transform. So what is the state of the art in telepresence? Probably the earliest work was towards this goal was by Takeo Kanade at CMU in 1997. They published some work called Virtualized Reality, in which they tried to reconstruct people interacting, multiple people, and for future observation inside virtual reality. But this was an offline process, and the first real-time system was built, among others, by Rosina Bashian et al. At Berkeley, 2005. But nonetheless, these were all laboratory systems in highly instrumented rooms. And the first big jump towards something that might actually be commercially viable for consumers in general was the groundbreaking work by Urtasun et al., Shahramazadi's group first in Microsoft and now at Google, in the holoportation effort that used the HoloLens as a display device for this sort of work. But all of these methods were what I would call measurement heavy, meaning they required instrumented systems and rooms. So in the case of the holoportation, it required, I believe, 12 stereo pairs to be mounted all around the environment. In contrast to this, in the graphics community, there was an effort to start to extend the sorts of models, these models that we see in games and in movie visual effects, for this sort of real-time interactions. And there was a stunning demonstration by a number of teams collaborating in the WikiHuman project in 2007 with Meet Mike, followed up by Epic Games with the Siren demo 2018, and then most recently with Digital Doug in 2019, which had a full, complete mocap suit and a demonstration as well. All right, and here's a recent result produced by our lab in Facebook Reality Labs. So this is a result.
Big ugly sucker at the door, and he said, "Who do you think you are, Lena Horne?" And I said, "No, but that I knew Miss Horne like a sister, and she told me next time I was in town to come and look her up." Well, next thing you know, it was Lena this and Arnold that, and oh, have you met the Duke? He's right over there. And that club was jumping and jiving. Ooh, that sounds good.
So this is a rendering using from our system in 90 frames per second in 3D. Obviously, what I'm showing is a 2D video, but this is actually something which you can experience in 3D in real time. And this is how this would be used is that there would be people in remote sites, as we had mentioned. Each would be wearing headsets, and they would have an experience with one another as if they were in a room talking to one another. So this is a real-time interaction captured by our system.
Well, what can your face do? Can you show us?
Well, I've always hoped you would ask me that question.
Mm-hmm.
So I have some pretty good, I think, mouth movement.
How about your eyes? Can you look left, right, up, down? Good.
Yeah, I'm gonna be surprised. Ooh. I think one of my favorites is puffing my cheeks.
The mouthwash commercial.
Mm-hmm. And rolling my tongue.
That's pretty good, actually.
Yeah.
Good.
Yeah, not a lot of people can do that.
Yeah, one sort of good test is, can we get through like the first few letters of the alphabet? A, B, C.
And you can see that this is an experience that people can feel in real time, see the other person in 3D, despite being in distances, right? And the core technology that we've developed, we refer to this as codec avatars. Codec coming from the term coder-encoder, right? That's used for compression systems. And the way we think about social interactions is that the two people are really transmitters and receivers of information in an information theoretic sense, right? We are transmitting information, which includes what we say, our facial expressions, our body movements, our hand gestures. All of these form a message that we're transmitting across distance. And we need sensors that pick them up. So in this particular case, we had instrumented the headset with cameras, and it takes that data from the transmitter, encodes it in some way, and we'll talk about what this function is, transmits that code across distances to a decoder, which then takes that information and decodes it into what the left and right eye of the person sees, and it gives the person an impression that they are there with the other person. Now, for reasons I'll explain in a little bit, there is also this dependence of the decoder. For instance, when I'm looking at you, how you appear to me depends on my state as well. And this is somewhat counterintuitive, so it's not a decoder in that classic sense, it's conditioned. And I will explain in a bit why this is sort of necessary and why it's likely to be a major feature of these sorts of interactive avatars in telepresence in the future as well. And then finally, you and I need to meet somewhere, right? Are we meeting where I am? Are we meeting where you are? Or are we meeting in a third location like the Eiffel Tower or some other conference hall? And that you need to relight the avatar to look that way. You need to re-sound the audio to make it sound like you're in an office environment or a cathedral or outdoors. And so codec avatars we developed them first in 2017. We upgraded, you can see some blurring around the teeth. We had some upgrades to improve the sharpness of the teeth, added hair in 2018, and then improved the eyes last year, along with first results in hands and bodies as well. So all of this is research work in progress, but we've been systematically trying to see if we can complete the entire experience of having an interaction with someone else. And so fundamentally, what is a codec avatar? So just like an autoencoder, it has two functions. It has an encoder and a decoder. And what the encoder takes, f of c, takes the sensor measurements from cameras, microphones, other sensing modalities, and produces a code. And this code is, of course, a vector of numbers that represents the state at which that person is in, right? And so you can think of these in many ways. Like the first value, if you tweak it, one way of thinking about it would be it might move my shoulder up and down. If I tweak another number, it might sort of pull my left mouth corner up and down. So those sorts of things, it's some sort of parameterization that encodes the state of the person. And on the other side, there's a decoder that takes this code and produces for it the sensing modalities that the receiver needs to see of the transmitter to make them feel like they're there with them. That would be what the person would see for the left and right eye, and what the person would hear in the left and right ear. So let's look at the decoder first, right? So the decoder is a function that simplistically produces the left and right eye output images, and it takes as input the code of the other person. So it's been encoded in some way. It receives this code, and then based on what the state of me, the viewer, the receiver is, it produces those two outputs. And of course, it depends on some sort of parameterization. A function has some sort of parameterization and weights. Our most sophisticated function approximators are neural networks. And so these would be the network weights. And of course, this would be different weights per person. So every person would have their personalized decoder. In other words, the transmitter, whoever is sending the information, would have their unique identity index that corresponds to those weights. And of course, as I mentioned, most broadly, we'd actually like to include the left and right ear as well. And this would also be conditioned on the environment. So the images that you see of the transmitter need to be relit and resounded to make it sound like you're there with that other person. And so that's kind of like the flow of information. That's the decoder part of the network I just mentioned here. Now, what does this decoder do? It's essentially in this particular incarnation that we've been trying to do, it's about 128 floats. And it decodes, there's one function that decodes the mesh to, in this particular case, about 23,000 values, each of which are the XYZ locations of this mesh. So each of these XYZ locations form one of the entries of this matrix. And then the same code that produces the mesh goes into another function that produces the texture. And the reason for this is that appearance depends on expression. In other words, if you look at the face of Sheikh over here, in this neutral pose, when he sort of scrunches it up, you can see the blood flowing into his temple areas and into his nose. And that's because the texture that your face has changes with expression as well. And so that same code that encodes the state of the transmitter is also decoded to produce the texture, right? So these are two separate sub-decoders. And that's what this looks like. That's the mesh that I'd shown earlier. This is the texture unwrapped to make it two-dimensional, and also, as you might suspect, to make it convolutional. And so over here, what you see, this is essentially like a map, like the map of a globe is unwrapped to make it two-dimensional. Similarly, the texture of the face is unwrapped to make it two-dimensional. And as we vary the codes, you can see both of these things co-evolve. They're decoded simultaneously, both the mesh and the texture. And so it's a shared code that generates the geometry and texture. Then this mesh and texture, they get combined in a simple renderer to produce the image. And the weights of this network is trained or optimized to reproduce the pixels that are observed by cameras looking at the person, right? So this is how we train this decoder. And over here, you can see there's a swipe going backwards and forwards that show you the relative quality of the decoded texture compared to the actual raw pixels. And this is where this concept of metric telepresence comes from. It's not that you try to produce something that looks right. It moves the left part of the mouth when the person moves the left part of the mouth, or smiles in the right way. It's not that. It is that every pixel that was observed has to be minimized, and that's the goal. You want to try to reproduce truth to the extent that you can. And so what does the code look like? This is a visualization of what the different numbers inside this vector look like. So if we take the first vector, first number, let's say any number over here, this one, it matches to this particular one. What we're doing over here is keeping everything else sort of like constant at the mean value. And for one of these codes, we're varying it to plus minus 2 or 3 sigma, I forget which one. And this is very common in PCA. You must have seen many visualizations of this sort for many subspaces. This is that same visualization, but you can see some interesting sort of differences here, right? The first one is that the movement is not linear. It sort of moves in this way, particularly over here you can see. It's not the typical linear movement you tend to see with PCA. And secondly, it's not symmetric either, right? So this is a much more interesting kind of texture to the encodings that these networks produce. Now, why was it that the decoder was dependent on my state? Why does it matter, me, the viewer? Why do I get to influence how your avatar looks like to me? And that's because of reflectance. So in other words, when you look at some surface that is not purely Lambertian, where you look at it from changes its intensity. And specularities, shiny things on surfaces are a very good example of that. As you move, they'll move with your viewpoint as well. And you can see this on the face, on the nose. You can see that as you change the viewpoint, in the front view, there are these two lobes. As you move further and further, those lobes collapse into a single lobe at the extremes. And so therefore, that's why it's conditioned on the viewer. Where I'm looking at you changes how you appear to me. And so to encode this, what we do is we add this view code, like where I'm looking at you, and that influences, that's taken into the texture decoder. Notice it only influences the texture and not the mesh, because obviously how your shape is, that's not influenced by where I look at you from, right? And so this is what that looks like. You have the core mesh, you have many different views, and this is that unwrapped texture. Now notice that when I play this, the geometry is the same for all. The views are all different. So you can see the textures are all different. And there are different parts of maybe if I move this here, you can see there are different parts of the face that the texture is decoded differently. I'll play that one more time. And the reason is because obviously these areas are not visible from this perspective. These areas are not visible from that perspective. Neural networks are famously lazy. They don't expend capacity trying to explain what they don't have to. And so this is what the end-to-end system looks like, right? So you can see the code starts, produces the geometry and texture, and then those are rendered to produce these images. And here we're varying the view code. We're changing the viewpoint. And as you see, as we change this viewpoint, the texture changes, and then the final rendered image changes as well. So as you change the viewpoint, the texture changes as well. All right. So how do we actually produce this? Where does the training data for this actually emerge from? And that's from what we call Mugsy. So this is a capture system that we have in Pittsburgh. It has 100 microphones, 160 high-resolution, high-frame-rate cameras, and about 450 lights. And it is the place in the center there is designed to try to capture, obviously, the light field emanating from a dynamic object. So it's a video, as well as we try to get as many viewpoints as we can. And what does the data look like? So you see here are a couple of views. Now notice each of these views, you can see the side, the back, the top of the head, the back of the head. We see all of these different perspectives on the person. And it's high enough resolution that you can actually really see details like what he had for lunch. And using this data, using purely multi-view geometry, we can reconstruct the three-dimensional structure of the person's face. So this is a frame-by-frame 3D reconstruction with no tracking going on. You can see we can get really nice detail on the face. And then subsequently, we can use these reconstructions and the texture to track the mesh of the person. We're also able to use state-of-the-art key point detectors that get, for instance, the teeth as well, nose areas, 2 different linings on the eyelid, and of course, the eyes and the iris. And this is the quality of tracking that we can get as a result. And this is sort of obviously zoomed into the side of the person's face. You can, in fact, track any hair follicle over here. It really, really sticks as it needs to on the person's face. And this is important. This is key because all of that subtle signal actually means something to us. We're very sensitive to it, and we're not always aware of what is or isn't important. So we really need to capture as much of it as we can. And this demonstrates the degree to which we are able to. And so we have this end-to-end pipeline that takes the input data from all of these cameras, reconstructs it, detects key points, tracks the mesh, and then finally learns the avatar, the codec avatar that I was talking about, the decoder that we spoke of. And so this is an example of a result.
Hi, my name is Steve Lombardi. For those that don't know me, I'm a researcher at the Pittsburgh lab working on codec avatars. The goal of our work in Pittsburgh is to create a system that enables social experiences in VR and AR just as you would have them in real life. When Yaser asked me to do the symposium talk, I thought, great, I'll let my avatar speak while I just sit on the couch. But I was told that I should probably show up. So please welcome Real Steve.
So you can see over here that the view was turning left and right artificially. That was all rendered by the system. And here what we're doing is we're reprojecting the codec avatar for these different people back into the images that were used to produce them. And what you're seeing there's a line that separates the real from the rendered, real from the rendered, real from the rendered. And we're going to swipe it past. After a while, the white line is going to disappear, but it's still swiping. And the more clearly you can see the white line or the sweeping, the less successful we've been. So let me play this. See the line disappears right now, but it's still sort of like swiping. And if you look closely, you'll see there is some detail that's lost. But to a large extent, it seems to be doing okay. And now that was the decoder. That was something that takes the code and produces what your left and right eye would see. The other half of this picture is the encoder. How do you actually represent the behavior of people in these sorts of codes? How do you extract that signal that the person is trying to convey, and what is that representation of the code? So this is the encoder part of the picture. And here's the challenge, right? So if you want to show the person what I am doing, if you want to show the receiver what the transmitter is doing, you need to wear this large headset on your head, and it occludes what your upper face is doing and to some extent what your lower face is doing as well. And that makes it very challenging to sense what the person is actually doing. So this is an example of one of these interactions.
So I was telling you that I believe in ghosts, and you don't because you believe in science.
Yeah.
So I think
So you cannot just put a webcam looking out into the person and actually hope to recreate on the other side what this person is seeing, because the face is obviously such an integral part of the experience. But this is actually just one flavor of it. If you want to get the whole body, there's also this challenge that I cannot stay in one place and just, when I speak, this is a constraint for me. I would like to walk around. I'd like to share that space with you, write on a whiteboard, maybe form 2 or 3 clusters if we're a large group, just like we do in a real interaction, right? Those are the sorts of things that 3D or virtual reality or artificial reality afford. But we have to be able to sense what the person is actually doing, and that's a pretty big challenge. And if you see, like in some of the works I talked about earlier, these experiences that they've demonstrated are all asymmetric experience, meaning it's only a one-way interaction. Only one side can see things in 3D. The other side has to have a nice, clean view of the person's face or the person's body, right? What we did was we took a stock headset and we modified it by placing cameras looking at the person's eyes, the mouth, and then the temple area over here. And you see these are the 4 views that we get. And in using the system, we try to infer what the person is actually doing with their face. So this is, like what we want to do is we want this face to produce this exact expression. But herein lies the challenge, right? What machine learning methods, what neural networks generally work well with are supervised learning problems, right? Where you have examples, lots of examples of input-output pairs. For this input, produce that output. In this case, if we had something that could produce, given these camera images, produce that code, we would be in good shape, or even the output. But we don't have this. What we can do is collect a lot of data of the person inside the headset with videos, and a lot of data of the person, the codes themselves inside our multi-view capture systems. This is a somewhat subtle problem, but there is no way while I have the headset on that you can collect the videos if you want to, but there's no way of actually figuring out precisely what I was doing inside those, except by looking at those images, but there's no external supervision that you can get. So we have this sort of unsupervised flavor over here where we have two bags of data without correspondence, but we need to learn a mapping between them. Right, so this is kind of, if we had this sort of data, it would be fantastic, but we have no real way of getting it. And so to solve this problem, we came up with the following approach. So given the sort of like input, and one of the reasons why I find this to be a very interesting kind of like result is, it's actually a way in which we can visualize gradient descent on a person's face, actually. You can see a facial expression evolve while the system is optimizing, right? So the first thing we do is we take the image data, we take the neutral face with the decoder, and we do a domain transfer because these cameras are in IR. We do a style transfer to produce what that texture would look like if it was in IR in this way. And then we have a differentiable rendering step where we render those images from the viewpoints of the cameras on the headset. And what we want to minimize is the loss between these sort of rendered images and the actual images taken by the headset itself. And that's what you see over here, like right in the center of the screen, right? And what you'll see as I run this is that this, as you run the optimization over the weights of the encoder. So you want to find weights of encoders that minimize the error here. And that's what you're seeing, it minimizes the error. So that's the first thing to look at. The second thing I'd like to ask you to look at is this face now. So as the optimization runs and the loss is minimized, you will see that she will reach this kind of an expression. Here her mouth is open, her eyes are open. Here her eyes are closed, her mouth is closed. As the optimization goes, she closes her mouth, closes her eyes. And then that sort of like propagates here to the domain transfer, produces the new images, and the loss is minimized. And so the gradient descent continues marching on. And now let me play a few more, right? So here you see the next one, mouth open in a smile. So she goes into the big smile from, again, the same initialization of neutral. Here, this is kind of like a growl of some sort. Here, it's like puckering your lips, and she gets to that as well, all through this sort of optimization. So the system is simultaneously using the decoder that we have, producing codes to supervise itself, and subsequently with that information, we can learn an encoder as well. And so this is what the output looks like. You can see this is the face, and now we're scanning once again against what the person was actually doing in the headset. And again, that's what we're trying to do. We're trying to minimize the pixel errors per pixel from what we can actually observe. In this case, the cameras in the headset. And here's what the live system looks like. So you can see he's wearing the system live and producing these results. And so this is the whole system end-to-end. The encoder takes the images from the cameras of the headset, produces this code. We take the viewer, now my viewing Israel in this case, and it produces the mesh and the texture. And then you render this to produce the view of this other person. And you can see this whole system working end-to-end. Again, we're changing the viewpoint here, but this is the transmitter making some facial expressions, and it gets rendered on the other side. And here's another result of Jason, one of the key researchers in this effort, Jason Saragi.
Hi, I'm Jason, and I'm a research scientist at Facebook Reality Labs here in Pittsburgh. What you're seeing right now is my codec avatar, digital representation of my face that captures my likeness in 3D, as well as my speech, my gaze, and my facial expressions.
So that's an example of what this looks like. And so this is once again that entire kind of like view of social interactions as a communication network, right? What we've been able to do is convert those movements, that audio, that all of that content into computable value, something which we can represent on a machine transmitted over the network. So the sensor in this case produces these images from the person's face. The encoder takes these images for both people. So this transmitter produced one in both sides, encodes it to produce these codes, one for each person. And then the decoder takes both of these codes in addition to the viewer's or the receiver's state, and then produces views for the left and right eye, which are then displayed using 3D displays. And this sort of thing is happening continuously, just like a regular interaction. It's continuously sending it. And this is one aspect, as a scientist, I find it very satisfying when you design, you have an artifact of design trying to optimize one criteria, and that artifact actually is ideal for a completely separate orthogonal criteria. In this case, The reason why we produce the codes, these bottlenecks in the network, are to encourage learnability, right? That's why we have these bottlenecks inside our networks. But in this case, it's another ideal case where you actually compress for transmission as well. These codes that we have are now actually compressed for network transmission as well. And in our case, it's oftentimes kilobytes per second that we're sending, probably tens or hundreds of kilobytes per second, well within network reach. And so this is what that interaction I showed earlier actually looks like on both sides.
So I was telling you that I believe in ghosts, and you don't because you believe in science.
Yeah.
So I think I watched too many ghost stories. I used to come home from school and watch Are You Afraid of the Dark every day. Did you ever watch that show?
Yeah, I watched it a couple times. I think I read some of the books too.
They had books?
Wasn't it? No.
Is that
I'm thinking of
Goosebumps?
I'm thinking of
Yeah.
Goosebumps.
And then this is, of course, another set of the version I showed earlier.
Have you told anybody about Yahtzee yet?
What's Yahtzee?
That's where we build a yacht and then we collect data on a yacht.
Oh, that's so clever. I like it. We should definitely do it. Now
Yeah.
we must do it.
I think we could.
Right. And so, of course, the last bit of this, which we're currently working on, it's work in progress, is how do we actually get these environments? What you saw right now were these sort of like floating heads in the background. The last key to this is how do we actually get environments in here so that the person looks and feels like they're in that location. And there's been a lot of breakthrough work by Paul Debovic over the last couple of decades on how to, in fact, actually relight faces and bodies inside different environments. And so we are also investigating along those lines how to actually relight faces, but in this kind of like encoder-decoder paradigm. And here are some early results. As you can see, we can recolor and relight the face by conditioning the network on some sort of representation of the lighting in the environment as well. These are very preliminary results, and hopefully we'll see progress as well. So what's next? Beyond these, one of the key obvious things is we have to improve the quality. We have to complete the avatar, not just the face, but we want to get the eyes right. We want to get the hair right. We want to get hands, bodies, acoustics right, and finally the environment as well, right? And so this is a paper that we will be presenting at SIGGRAPH this year on improving the quality of the eyes. This, what you're seeing over here, is also fully a render, but the eyes are obviously of much better quality. And then here's a paper we presented at CVPR, I believe, a year ago or 2 years ago, where we can actually reconstruct strand by strand the hair on the person's head. And here you can see it's actually strand by strand accurate. Once again, that notion of metricity. I'm not sure what the word is. And we can use this then to produce kind of many different hair types. This is another approach to it called neural volumes that can actually produce different hair types. And this is, again, viewable in 3D in real time as a playback. Now, for the full body, we've built systems to try to record similar sort of multi-view data of the body. This is called the Sociopticon. I won't go through the whole thing, but you can see it's a dome. And internally here, you can see each of these are microphones as well, which I'll talk about in a second. And what does the data look like? You can see once again.
This is a construct. It's our loading program. We can load anything from clothing to...
We can see the person from many different viewpoints.
Training simulation.
And once again, we built this pipeline that takes the person, reconstructs them in 3D, tracks them as well, like precisely. And it's the entire set of key point detection, mesh tracking, and then learning and avatar decoder as well, once again. The same pipeline that we built for faces, we have extended it to full bodies. And here is a result, early result of what we can produce.
We can load anything from clothing to equipment, weapons, training simulations, anything we need. Is it really so hard to believe? Sorry, this one is for the audio demo.
Here, everything, the person, the face, the hands, the body, the background, all of these are rendered pixels. That's all real, and you can actually observe this currently only the decoder in playback, but you can actually observe this in 3D in real time as well. Now, beyond the full body and completeness along that direction, we're also looking at audio because it is, after all, a really important modality of interaction. And our cognitive engines tend to be multimodal. And when multiple modes or multiple sensors coincide on evidence, we tend to believe it much more. So if, for instance, the sound is coming in a direction from the same place you're seeing the person precisely as you would expect to hear it, you're much more likely to, believe or feel like that interaction is real and indistinguishable from reality.
This is a construct.
So in our system, we have about 1,700 microphone channels. And from that, we can reproduce the audio field precisely inside the event space of the socio-opticon. And you can see that over here. What we've done at this yellow point is produce the audio signal. And this is the spectrogram of that signal. And if I play it, you'll see what we can do.
This is a construct. It's our loading program. We can load anything from clothing to equipment, weapons, training simulation, anything.
And that's, as what you have seen here, is in fact the audio field as the person is moving. We have, for the first time, probably the first time anyone has been able to accomplish this, get the detailed movement of the person's body as well as the audio field in that space. And so when he snaps his fingers, there are two very interesting things that we can do. The first is, if we go in and slow things down, you can see the wavefront that emanates from that snap emanating out there. We can sweep and analyze this in frequencies as well. Look at the different bands of frequencies as you see over here. But there was something else when I was looking at this again and again that I noticed. When you snap your fingers, in fact, there's one wave emanating out. There's another one emanating and interacting with the speaker's body, at which it bounces off. And you can even see that captured, which is really interesting. So there's the wavefront, and there's another one that comes with a certain phase offset and bounces off the body. It comes out, and this captures that as well. So it's very early, it's interesting, but it's really powerful, especially when there are multiple people in the space, especially when there's a reverberant environment. It's really important to capture these sorts of effects. All right, so that's the entire picture right now where we are. And I wanted to kind of like close with reiterating the importance of subtlety over here. What we're showing over here, this is a real image. Here, what we're doing are two different encoder decoders, right, which produce realistic output, and we're snapping between the real image and the original image and the rendered image. And you'll see both of these seem like viable expressions as you're snapping between them, but only one of them is real. And I want you to kind of like just look at it and see the difference in signal these very subtle changes make. Like what these expressions mean to you are in fact something different. And when you think of a communication network as transmitting information back and forth, these small perturbations are likely to change the nature of the conversation in a significant way, because these small changes actually carry a lot of information for us. So I'll conclude with a statement that the next step, hopefully from video conference, will be metric telepresence. In the paper I referred to earlier, there was a quote that said, in a few years, men will be able to communicate more effectively through a machine than face-to-face. And this was written by Licklider and Taylor in 1968, a long time ago. And obviously, while this has not come true so far, there's a real kind of opportunity, I think, in the next few years for us to make genuine progress towards this, where it does feel like you're able to have interactions that are indistinguishable from real interactions, even though you're very far away from the other person. And oftentimes when people think about AR and VR, they think of it as one more technology in a series of technologies that will make us more disconnected with the people around us. But I think this notion is profoundly mistaken. The real potential of AR and VR is that it will connect us in ways we've never seen before, and hopefully bring the world closer together. With that, I will conclude my talk. Thank you for your attention.
Let's see. So thanks, Yaser, for the great talk. These were awesome results. There were also really a lot of positive comments about the results in the YouTube chat, especially about the high quality. We also have one or two questions. So let me start with that. So one question was like, how does the object deal with like really, how does the system deal with really specular objects? Like maybe the eyes are a good example, or the teeth.
Yeah, I think that's an excellent question. I would say right now, not so well. So in most of the results I showed you right now, one of the big so-called cheats over here are that we're baking in the illumination on the texture itself. So it makes it look more real. one of the key research efforts I showed very early results on is the relighting work. And over there, particularly with the specularities of the eye, those are things which we want to try to get them so that when we are in a new environment, your eyes and your entire face actually get relit. It's an important question as well, because most people think specularities, it's just the eyes. Eyes are important, but the face oftentimes is oily. The teeth are shiny. You have glasses that you're wearing. So there's a lot of, of that, not necessarily the extreme specular effect, but specular artifacts on the face as well. I would say this is an open area of research that we're currently working on. And I'll also note that it is sort of like a real challenge. What these networks, particularly when we have losses like an L2 or L1 loss, what it does is it blurs things out. So to get real detail and quality, that's, I think, going to be a challenge, an interesting one. And I hope that we see some sort of ideas come in from classic reflectance research into the work we're doing as well, to see how we can address this issue.
It's really interesting that you brought up the glasses, for example. There were also 2 or 3 questions about accessories in general and how you plan to handle them. Like there could be a necklace, there could be glasses, somebody could be wearing a hat.
Yep. I think there are 2 thoughts I have on this. I mean, you can extend this to clothing as well, of course, right? With the full body clothing is another issue. These are the sorts of things. There are some interesting results from our group in collaboration with FAIR, and there are other papers as well. The PIFU HD work I would refer you guys to. It's interesting that there are some results showing that you can actually parameterize the appearance of clothing. I believe there's some good work from Gerard's group in reclothing, from Michael Black's group in that direction as well. So there is kind of like a hope that you could condition on the appearance as well. But the second thought I had is that it sort of raises a very interesting question. Like, to what extent should you be able to modify your appearance inside these interactions, right? So for instance, if someone was to say, okay, can I change my hairstyle? It's very reasonable. I think we'd all agree with it. Can I wear makeup? Again, nobody would sort of like contend that that's controversial. But then you start to say things like plastic surgery. Can I change the way I look? Can I look more like Michael over here, or Christian, or Armin, right? Can I change my appearance? Now I'm somehow violating someone else's space. In real life, this is not really an option because obviously physics stops us. But in virtual spaces, this is a real concern. So it's kind of like an interesting a question and balance, and this requires us to think deeply. And I think we have to think about it in anticipation of the technology itself. It's an important question, not just of technology, but about ethics, maybe even philosophy, a little bit about how we should be designing these systems.
Cool. There was one more question. So this was mainly about sensing modalities. So in Pittsburgh, there are these really impressive systems with like a lot of color cameras or grayscale cameras. So the question was basically if there's a plan to use other sensing modalities too. For example, like IR cameras or these heat cameras, or maybe even like attach IMUs to the body in addition.
In our sort of work, we don't have direct plans to do that, but I do feel like it's a very important area of work, right? There are other modalities like EEG that we've looked at before. We were looking at it to see if we can get some sort of like complementary signal. It turns out it's very good for eye movement. We didn't really explore it fully in that direction, but that was one sort of extraneous modality. My view is kind of, no information can ever hurt. If you're doing things properly, additional information will always help you if you know what you're doing, right? The question is the effort involved in including those, does it provide you with enough information or not? I particularly think as we get into more sort of like full body movements where contact, occlusions, those sorts of things become much more prevalent, I think we'll have to rely on multiple modalities and explore a bit more in that direction. There was some interesting work from MIT, I think last year, a couple of years ago, about wireless sensing as well. I thought that was a promising direction.
Okay, awesome. Thanks again for the really nice talk, really impressive results. And we will have a short break now in the workshop and then continue afterwards in 10 minutes. Thank you.
Okay. So thank you everyone for rejoining. We are now in the main paper session of the workshop, and we have 4 exciting papers that will be presented. 3 of them were submitted to the workshop and one of them is invited from the CVPR main track. So we'll begin with the first talk, which is Semi-supervised 3D face reconstruction learning from unconstrained photo collections. And the speaker is Zongpa Gao. So Zongpa, if you're able to share your screen.
Yes. Can everyone see the screen? Yeah.
Begin.
Hi, everyone. My name is Pai. Thank you for the opportunity. I'm going to present semi-supervised 3D face representation learning from unconstrained photo collections. We want to reconstruct 3D face from a single RGB image. 3D face includes shape, lighting, and albedo. We also want to disentangle the identity and expression so that we can achieve expression transfer and many other downstream applications. Molecular 3D face reconstruction enables technology for many applications, such as CG actors in VR and games, virtual makeup, emoji, biometric detection, and facial image editing, and so on. Molecular 3D face reconstruction is an ill-posed problem. 3D morphable model often serves as a strong prior assumption. 3DMMs are linear parametric models learned from 3D face scans using PCA to model the 3D shape and texture. Shape can be expressed as mean shape plus identity components plus expression components. Here's an example of adjusting the identity parameter. Similarly, we can adjust the texture parameter to change the facial texture. Many 3DMMs have been built, including BFM, Face Warehouse, LSFM, and so on. With a linear 3DMM, the problem of 3D face reconstruction from a single image is to find the parameters of identity, expression, texture, lighting, and pose, so that when we render a 3D face, the rendered image is close to the input image. Two types of methods are often used. For optimization-based method, they randomly initialize the parameters and iteratively update the parameters by solving an energy minimization problem. And for learning-based methods, they train neural networks with labeled facial images and predict the parameter directly. Labeled image means a facial image has the corresponding 3D shape. However, optimization-based methods are time-consuming and usually take a local solution. And learning-based methods need a large amount of labeled images, which is very expensive to obtain. Importantly, both methods can only find solution limited by a linear 3DMM and cannot generalize in the wild. And Chen proposed a nonlinear 3DMM. Given an input image, they use CNN encoder to regress pose, albedo, shape, and lighting parameters. Then use albedo and shape decoder to regress the 3D face albedo and shape. Finally, they use rendering layer to render back the image. However, the model is only trained on 300 WLP dataset, which is generated based on a 3DMM. And they didn't separate the identity and expression of the 3D face, which disables many applications, such as expression transfer. And in this paper, we propose a nonlinear 3D face model learned from unconstrained photo collections. It is easy to obtain large amounts of unconstrained photo collections online, such as from Facebook, Instagram, WeChat Moment, and so on. And for each person, the identity is consistent across different photos, and each person has the same facial albedo. Well, different photos have different expression and lightings. A monocular 3D face reconstruction is ill-posed. Self-supervised learning from unlabeled data through inverse rendering is not sufficient. We apply semi-supervised training on hybrid batches of labeled and unlabeled face images. We chose 300 WLP for the labeled data and celebrity dataset for the unlabeled data. Also, we apply adversarial training for adversary training to ensure the generated face is not far from the distribution of human face. Since the distribution of human face is unknown, we sample the real data from 3D-MM. The pipeline of the proposed method is as follows. First, given an RGB facial image, we use CNN encoder to extract the identity, expression, pose, and lighting code. Then the identity code is fed to the albedo decoder to generate 3D face albedo. And we concatenate the identity and expression code and feed it to the shape decoder to generate 3D face shape. At last, we render the 3D face to get a rendered image. The proposed pipeline is different from Chen's in two aspects. First, instead of using multi-layer perceptions, we use GCN for decoders. Second, we separate the identity and expression representation, and the facial albedo only learns from one's identity. How to train the network? We impose 8 losses as constraints. The first is face recognition loss. Different photos from the same person should have the same identity code, so that it is invariant to different expressions, lightings, pose, facial occlusions. And center loss is introduced to enhance the identity extraction. And the second is adversarial loss, which is used to make sure the generated 3D face shape is not far from the distribution of human face. And here are the results of aberration tests. Since the 3D shape in our model is not constrained by 3D-MM, it can potentially be deformed in any shapes. When without the adversarial loss, the shape is distorted on the edges. You can see from the blue circle. And when without the face recognition loss, the shape has smaller mouth opening compared with the full model. So it's not robust to exaggerated facial expressions. The third loss is photometric loss, so that the rendered image is close to the input image. Here, we exclude the facial occlusions, including hairs, glasses, microphone with a mask. The fourth one is albedo symmetric loss, since human face is normally symmetric, and this is important to ensure the albedo is separated from lighting and shade and facial occlusions. And the fifth one is sparse landmark loss, which is crucial to learn face pose efficiently. We add gradient different loss for landmarks to get more accurate mouth and eye opening. A novel shape smooth loss is used. The conventional smooth loss causes undesired artifacts on nose, mouth, eye, and edges where the vertices do not satisfy the Laplacian smoothing constraint. We add temperate smooth loss to resolve this problem. And here are the results of aberration test. When using conventional smooth loss, the vertices inside the nose came out of the nostrils. You can see from the blue rectangle. And for the images from 300 WLP, they are trained in supervised manner. Moreover, we introduce a pairwise shape loss to help disentangle the identity and expression representation. The pairwise shape loss takes a pair of images from 300 WLP and exchange the identity and expression code to generate new face shapes for supervision. And quantitative results show that the proposed method outperforms state-of-the-art monocular 3D face reconstruction methods and is comparable with MVFNet, which is multi-view method. And here we can see some of the results. We can reconstruct 3D face with separate components, shape, albedo, and lighting. Compared with other methods, the proposed method is more realistic, especially from the perspective of the frontal view. And here are the results of comparison with Chen's work. The proposed model achieves better performance across various conditions, different expression, pose, and occlusions, lighting, and ethnic groups. From the first row, you can see the mouth opening is more accurate. Our method is more accurate compared to Chen's method. And here is we can also reconstruct video sequence as presented here. The video has diverse lightings, pose, and expressions. And the reconstructed identity are consistent across over the frames. You can see from the second column. And here's another video to demonstrate the robustness of the proposed method. And using this method, we are able to transfer one image's expression, pose, and lighting to another image. And many other applications can also be used, can also be achieved in the future. So here is our conclusions. We proposed an efficient semi-supervised and adversarial training process to fully explore unconstrained photo collections and go beyond the limitation of linear 3D compared to many other methods that regress parameter of 3D and train that was only trained on 3D 100 WLP generated from 3D And second, we design a novel framework to extract nonlinear disentangled representation from an image with the help of face recognition loss and shape pairwise loss, compared to Chen's work in which the identity and expression are not disentangled. And also, the experiment showed that our model achieved the state-of-the-art performance in face recognition and face reconstruction task. Thank you very much.
Okay, thank you for your talk, Pi.
So should I stop sharing the screen, or?
Yeah, I think you can unshare your screen. In the interest of time, we can have questions in the panel discussion later, just because we fell behind a little bit. But if people want, is that okay?
Yes.
Yeah. Okay. Cool. And just for the audience as well, if you have questions for the speakers, please submit them in the YouTube channel. So we'll now move on to this. So I guess we thank the speaker, and we'll move on to the second talk in the paper session. So Marcus, are you able to share your screen? Brilliant. And so the second talk in the paper session will be bilinear parameterization for differentiable rank regularization, and it's going to be presented by Marcus Valtonen. Marcus, over to you. Marcus? We need to unmute you.
Thank you, host. Hello, my name is Marcus Valtonen, and in this paper, we propose a novel framework for low rank inducing penalties in which many popular non-convex regularizers can be reformulated into smooth objectives. Let us first look at two different problem formulations. To the left, we have a standard rank optimization problem with known closed form solution, and to the right, we have an equivalent bilinear problem formulation. Now, the bilinear problem formulation has an advantage over the linear counterpart in the sense that it is twice differentiable, whereas due to the rank constraint, the linear formulation is non-convex and discontinuous. We do, however, introduce additional stationary points when using the bilinear parameterization. Now, a popular approach to circumvent the difficulties of the rank function is to convexify the cost function by using the nuclear norm. It is also well known that the nuclear norm has a variational formulation, which can be utilized in a bilinear framework. Now, returning to our previous example, but replacing the rank function with the convex counterpart gives the following cost functions. Here we have taken the liberty to consider a linear operator A instead of the identity operator, as in the previous slides. Cost functions like this has been used for multiple applications utilizing the linear problem formulation. However, there is no longer a closed form solution, and in general, it is non-differentiable. For the bilinear counterpart, on the other hand, nothing has changed, really. It is still twice differentiable at the cost of introducing additional stationary points. Here we see some of the advantages of using a bilinear framework. Now, it is not entirely without complications to use the nuclear norm as a convex surrogate for the rank function. In this example on the slide, we show the singular values of x0 and the corresponding singular values when truncated using the SVD. This is the hard thresholding shown in red. And simultaneously, we show the solution obtained using the nuclear norm, which is the soft thresholding. We see that in order to suppress the noise, we are required to suppress the true signal equally hard. And this phenomenon is called shrinking bias. Now, to address these issues, robust cost functions that act on the singular values have been proposed. And in order to penalize small singular values proportionally harder than the larger ones, the functions that you use are typically concave, having non-increasing derivatives. So to the right, we show some examples of these penalties acting on singular values, where the dashed lines correspond to the nuclear norm. But in doing so, the objectives are typically non-differentiable and often discontinuous, which requires first order or subgradients or splitting schemes. It is well known that such methods exhibit slow convergence for ill-conditioned problems. This leads to the work in our field, and in summary, our main contributions are a new, stronger, non-convex regularizer for bilinear parameterization with less or no shrinking bias, and we propose a new iteratively reweighted VORPRO algorithm optimizing accurately quadratic approximations. And we have a handful of theoretical conditions that guarantee optimal recovery under the restricted isometry property, the RIP constraint. And finally, an experimental evaluation that shows that our method outperforms state-of-the-art methods on several real computer vision problems. We will briefly go through the theoretical contributions. We consider what we call the pseudo-singular values that mimic the behavior of the singular values when we have access to the bilinear factors. Here, gamma I is the ith pseudo-singular value, which is the mean value of the length of the ith column of the bilinear factors B and C respectively, sorted in descending order. Now, I want you to note that gamma depends on the factorization, whereas sigma, the singular values, are independent of it. However, note that by recomputing the singular value decomposition, as is shown here in the example, where we split the factors B and C using the left and right singular vectors and the square root of the singular values, we can enforce that the pseudo-singular values are equal to the singular values. So they do have a lot in common. Furthermore, we show that by replacing the singular values with the pseudo-singular values, we get a more general variational statement than has previously been known for the nuclear norm. This result ensures that there is no loss in transitioning from a linear framework to our proposed bilinear framework for a large family of non-convex regularizers. And in return, you get the twice differentiable objective and have access to second-order methods for your optimization schemes. We will now jump into some of the applications of the proposed framework. One issue with many test cases in papers dealing with low rank regularization is that they are made for low-level imaging problems, such as denoising and image painting, where weak penalization is enough to obtain good results. This is not the case for structure for motion, where the missing data patterns typically are highly structured, as in the example here on the slide. Instead of having normally distributed missing data, which is illustrated to the left, a common situation in structure for motion is to track objects over several frames, leading to patterns such as the one to the right, when the algorithm loses track of the features. Now, we have compared our method to state-of-the-art methods on synthetic missing data patterns and outperform many of them. On this slide, we show the uniform data pattern with and without noise. Here, the error is measured as the difference in Frobenius norm, normalized by the ground truth, which is also measured in Frobenius norm. And as we can see, we are able to get perfect results for noiseless recovery and best results in all categories. Similarly, for the tracking failure data pattern, we found ourselves outperforming most methods, sometimes by far. But now, let us look into some applications with real data. The pseudo-object space error, or POSE objective, was introduced by Hong and Sack in 2018 and combines affine and projective camera models by utilizing a control parameter eta, which determines the impact of the respective camera model. This objective has proven to be robust and insensitive to initial solutions, and therefore it has been suitable for initialization-free bundle adjustment. So now the structure from motion problem has a rank 4 solution, but instead of enforcing the rank constraint, we replace it with a low rank relaxation. By not enforcing the rank constraint, we demonstrate the ability of the methods to make accurate trade-offs between minimizing the rank and fitting the data. We use two real-life datasets with various amount of cameras and locations in 3D. On the door dataset that we show here, there are 12 images, resulting in seeking a matrix of size 36 by 8,850. The regularization parameter is varied, and the resulting rank and data fit is plotted in the figure here to your right. To visualize these results, we consider the best rank 4 approximations and show the reprojected points and the corresponding measured points obtained from the best and the second best methods. In both cases, our method performs best, and the iteratively reweighted nuclear norm, IRNM, performs second best. As we can see, the second best solution does not yield an accurate reconstruction, whereas ours is more or less flawless. This can be seen by these red circles and the corresponding green dots inside of them. These are the measured points and the reprojected points. And much similarly, but for a different data set, we have 69 images, and in total, the corresponding low rank matrix is of size 207 by 1148. And by ocular inspection alone, our rank 4 solution is outperforming all the other state-of-the-art methods considered. Now, interesting for this workshop, the same approach works well for non-rigid structure for motion. In this example, we use the CMU motion capture or mocap dataset with orthographic cameras. The rank of the solution controls the complexity of the deformations of the object shapes, and the cost function used is the one made famous by Dye and other, 2014, I believe. But instead of using the nuclear norm as in the original implementation, we replace it by the regularizers proposed by the various methods. And as in the rigid structure from motion case, our proposed method yields superior data fit for all rank levels for all problem instances. Now, I just want to, in the remaining slides, go through some other applications that we have tested with our framework in. And here's an example of background extraction with missing data and a pan-tilt zoom camera, which makes the background non-static. On the top row, we have the original images. The mid row is the data, where black entries are the missing data. And on the bottom row, the extracted background. We can see that the background looks aesthetically pleasing, and we can confirm that our method is on par with the other state-of-the-art methods. Finally, photometric stereo with missing data. Here, the ground truth is shown to the left. Missing data mask is the colored areas, yellow and magenta, and the solution obtained using ADMM and our bilinear framework, respectively. Now, the interesting part is that the cost functions here are equivalent in both cases, but ADMM returns somewhat of a very non-physical rubbish solution, whereas our bilinear approach actually gives something that is ocularly pleasing. So these are exactly the same cost functions, but ADMM as an optimization method is stalling and cannot come up with any solution that is acceptable for these applications. Now, I just want to wrap up again our summary. We have a new, stronger non-convex regularizer for bilinear parameterization, and we use it in a reweighted VARPro algorithm. We have some nice theoretical conditions that you can read about in the paper. And we have tested this on several different applications. They are beating many of the state-of-the-art algorithms available. Thank you, everyone, for listening.
Thank you, Marcus, for your talk. Very interesting, and it's great. It was a great presentation and a fascinating paper to read. Again, just in the interest of time and getting back on schedule, if we can have questions for you in the QA session at the end.
Yes, that's perfectly fine.
Brilliant. Thank you.
I will remain here.
Thank you. Okay, well, thank you very much for your talk. And we will move on to the next talk. Again, please submit questions in the YouTube comments section. So we've had to change the order slightly due to a connection problem with the listed third speaker. So we will be moving to Sinead Kearney, who will be giving her talk on RGBD-Dog, predicting canine pose from RGBD sensors. And this is an invited talk from the CVPR main sessions. So Sinead, if you're able to share your screen.
Yep.
Brilliant. Okay.
Okay, thanks. So yeah, my name is Sinead, and I'm just going to talk about some work we did predicting dog shape and pose from RGBD cameras. So our main contributions are, this is the first method to predict shape and pose of dogs from depth images. We do this through a combination of a stacked hourglass neural network, and then we refine the prediction using shape and pose priors. And as part of the paper then as well, we're releasing a data set, a multimodal, multi-view data set of dog motion with a ground truth skeleton and marker 3D information. So to start off on why we chose dogs, there was a few reasons. It's an interesting problem because there's such a wide range in shape and size within a single species. They're relatively easy to source though, and we can bring them into the motion capture studio, and they can be directed to a degree during recording in order to acquire various motions of the subjects. There's also some pre-existing RGB data sets of dogs, so we think this shows that there's an interest in the community in predicting this type of information about the animals. So I mentioned that our method is in two stages. Our first is a network prediction stage. First of all, we use real dog data to generate synthetic images, and we use these to train our network. The network is trained to produce 2D heat maps, and from these heat maps, we extract 3D joint information. I'll go into this in a bit more detail in a minute. And then the second stage is our refinement stage. We take these 3D joint locations and we calculate the bone lengths of the skeleton. We take these bone lengths and use a PCA shape model to generate the dog that best fits these bone lengths. So now we have the dog skeleton, and we use a pose model called a hierarchical Gaussian process latent variable model to pose a skeleton such that it best fits the 3D joint positions that the network predicted. The network we use is just a standard stacked hourglass network. We chose this because it has been used by many other authors, and it has been shown to give good results for humans. So we made the assumption then that it would also be applicable to dogs. The HGPLVM is a generative model. It can be used to represent multidimensional nonlinear data in lower dimensions. The hierarchical version of this model means that we can exploit this skeleton structure in the dog motion data. So basically, sorry, I'm getting this up. The model is trained using joint information, so we represent it as rotation and translation. We have to use translation in the model because unlike humans, dogs don't have clavicle bones, and this means that their shoulders can actually move in 3D space, so we need to represent translation in the model as well. Because our model represents the pose in rotation and translation, it means we can use skinning methods then to apply the model output to a mesh. So this is just a visual representation of the model. On the left, we are just moving one limb of the dog, so this corresponds to one node in the model. But on the right, we're moving about in the top node of the model, and it's generating an entire pose of the skeleton. So what this means is that our method, we can first estimate the global pose of the dog and then go into each node in the model and separately refine each limb of the dog to best fit the network predicted joints. So we also use a shape model. This was created using a combination of photogrammetry scans of dogs and laser scans of toy dogs. The model represents dogs in bone lengths, in skeleton joint rotations, and the neutral mesh of the dog. We modeled the skeleton joint rotations because we feel that the neutral pose of a small squat dog is very different to that of a tall, thin dog. In order to make sure that our method works for real images, we want to be able to train it with realistic noisy images, noisy synthetic images. To do this, we use the renderer from InteriorNet by Lee et al. So we show here on the top row, this is real images that we recorded of the dog from the Connect. And on the bottom, we show the corresponding synthetic images that the renderer created. So in order to generate our heat maps, this is the method we're using. We're taking the skeleton in 3D space and we're taking our camera parameters and we're projecting them into 2D space. So for this joint here, we have the information, we have X and Y image coordinates, but we also have the depth value of the joint. So we refer to this depth value as Z. We normalize the depth of each of the joints using a 2-meter cube located at the root of the dog. And then we represent these X, Y, and Z values in 3 2D heat maps, as shown. And we use this combination here on the right because we performed tests and this was the combination that gave us the most accurate results. For real-world data, there's a few more options, a few more steps we need to do. We need to be able to locate the dog in the image and to create an accurate silhouette mask of the dog. For the moment, we were looking at pre-trained networks, but we ran into an issue where there's no pre-trained networks that can detect a dog in the image. We did find some RGB segmentation networks, and we looked in particular at Mask, RCNN, and DeepLab, but neither of these were completely acceptable, gave acceptable results. We found that the Mask RCNN was much more accurate at locating the dog in the image, but the mask that DeepLab produced when it did detect a dog was much more accurate. So what we decided to do then was to combine the two masks, where first Mask RCNN is used to locate the dog in the image. We crop the image then to this general area of the image and give it into DeepLab, and DeepLab gives us then the final mask of the image. So this is an example of what I mentioned, where our original image here is on the left. And we give this to Mask RCNN and it gives us the red mask of the dog. There's some areas around the legs that aren't quite close to the dogs that we'd like to be more accurate. So we've cropped the image then on the right and we gave it to DeepLab, and DeepLab gives us this purple mask. And you can see particularly under the neck, it matches the legs much more closely than Mask RCNN. So now we have the mask as the RGB image, but we need to be able to apply it to the depth image. To do this, we apply the homography matrix between the two sensors in the camera. And we get the mask on the left. So given our raw input image in the center, we apply the mask to this. We crop and scale the image accordingly so that it will be appropriate for input to the network, and that gives us the image then on the right. This is some example of the final results produced by the pipeline. On the top row, we have the 2D image, the depth image, and we have the projected 3D skeleton shown in this. And on the bottom row, we're showing the 3D dog skeleton from 2 different viewpoints. And yeah, as I mentioned, because our model produces joint rotation and translation, we can also get the manipulated dog mesh as well as the skeleton joint locations. We wanted to be able to compare our method with another method, but we ran into an issue where no one else is predicting dog shape and pose from depth images. So instead, we compare it with the method by Biggs et al. This team, though, is predicting dog shape and pose from sequences of silhouette images. So we acknowledge that the comparison isn't exactly fair, but it still gives us some sort of baseline to work from. So our result here is shown on the right-hand side of the screen. We use 2 different metrics to calculate the accuracy of the pipeline. And we also calculated for various sections of the skeleton along with the entire skeleton itself. And as expected, because depth images contain more information than binary images, we did get more accurate results than Biggs et al. For the most part. Sometimes they got better results for the tail, but for the entire skeleton, ours tended to perform much better. We also show on the left the structure of the dog skeletons. So ours is the skeleton on the right-hand side, and we believe that this is much more representative of a biological skeleton of a dog. So we believe this has just advantages in itself that it much more closely matches a real dog. Out of interest, we also tested the pipeline with images of animals that weren't dogs. We found that if the pose of the animal was quite close to that of what we had in the training set, then the network and the pipeline itself produced quite good results. The image on the right-hand side is the final skeleton and mesh produced by the pipeline. And the column next to this then is the meshes that were used to generate the synthetic images. And unfortunately, we don't have the ground truth skeleton for these meshes. They were just 3D point clouds. So we're only able to compare the results visually, but we do think that this is promising for future work. But unfortunately, even if we're testing the network on dogs, if the pose is very different to that, what we had in the training set, then the network is not really able to cope with giving it a sensible prediction. So for example, we didn't have any training data where the dog was sitting down or lying down. So this is the type of result the network will predict. But we believe that if our training set contains more varied motion, then these results will be improved in the future. So I also mentioned that we're releasing a data set along with our paper. This is multimodal, so we're giving RGB images, 4K and HD images, and also depth images from the Connect. There were some issues recording from the Connect, so it's only at 6 frames per second, but the 4K RGB video is at 60 frames per second, as is the skeleton information and marker information. So we're also giving the ground truth skeleton and mesh of the dogs as well. These are the dogs available in our data set. So on the left, we have 5 dogs. And for each of these 5 dogs, we have the five common motions. And we also have a random test sequence for each of these dogs. And on the right-hand side, we have 2 dogs that just have pure test sequences. And we chose these dogs because we felt that even for a small number of dogs, that they gave quite a large range in shape and size. And some more example images from the data set, we had to use various props in order to be able to record different motions from the dogs. So things such as a small table or jump poles. And on the bottom then is just an example of 5 frames apart of a dog jumping up onto a table. That's the sort of images that we were recording. And then these are the different modalities in the data set. So here we're showing the mask applied to the image, the projected skeleton, the projected markers from the motion capture suit, and the bounding box of the dog. The link here at the bottom is where you can access this data if you're interested. We also provide just some example code to help you make use of the data. So things like importing the animated skeleton and mesh into Blender. So we believe there's a lot of potential directions we can go with this work. One thing I mentioned was that we'd like to be able to have more variation in the poses in the training set. And this will help us to be able to fit to those images, such as the dog lying down or the lying down. At the moment, we're only solving frame by frame, so there's actually no temporal constraints in the pipeline. So we believe that incorporating this would give us much more accurate results. There's also some issues using the RGB mask and applying to the depth mask. We feel this isn't ideal, but it's something that we were doing for the time being. Our pose prior is currently in the form of HGPLVM, but we think that using a general adversarial network could give better results as well. And we'd also like to be able to record different species and test out the pipeline results on these. That's it.
Thank you for your talk, Sinead. So we have some questions, I guess. One of the questions that I have is about, so like dogs come in a huge variety of shapes and sizes.
Mm-hmm.
And I was interested to know about the construction of your PCA model. In particular, like some dogs almost have no tail at all, whereas other dogs have large tails. So how well do you feel that you've covered the range of dogs within your model?
So what we decided to do was keep the number of bones constant throughout all dogs. So for example, some dogs had a docked tail, but we still gave the dog the same amount of bones in the tail. We just made the bones very short. We just decided that was the best way to handle it, rather than to have different number of bones per dog.
Cool. And then I guess what are you what applications are you looking at for this work? Because I guess there's a huge amount of interest in animal welfare applications and things like that.
So I think things such as, CGI dogs in videos and games are kind of an obvious step, but also there's things like there's papers I've seen where they're using motion capture to detect lameness in horses, or just to kind of study the gait of an animal over time. Maybe if a dog has a prosthetic limb, you could track how well it's recovering over time.
Oh, and I think we have a question on the YouTube. No, there's not. Okay, brilliant. Okay, well, thank you very much for your talk, Sinead. It's a fascinating piece of work. And good luck in the main track of CVPR.
Thanks.
Okay. So, unfortunately, we've had connection problems because of what happened earlier. So, for the next talk will be given by a pre-recorded video. So, Christian, if you're able to share the video. And so, just lost the...
Hello, everyone.
Okay, so the
Thank
talk
you for your interest in our paper.
Is the Vertigo Effect on your smartphone, Dolly zoom via single-shot view synthesis. And the presentation is by Yangwen Lang, and we hope that they'll be able to join us later to discuss their work.
Paper with title, The Vertigo Effect on Your Smartphone, Dolly zoom via single-shot view synthesis. This work has been done by joint effort of Yangwen Liang, Rohit Ranade, Xuanquan Wang, Dongwon Bai, and Jungwon Lee from Samsung Semiconductor Incorporated in San Diego, California. These days, cameras on a smartphone are more sophisticated than they've ever been. Mobile phones now come equipped with multiple cameras of different modalities. A typical setup may include 2 or more cameras with different focal lengths providing different field of views. In addition, a dedicated depth camera or sensor to provide long-range high-accurate depth information within the scene is also very common. Such setups take user photography to next new levels, and open up the possibilities of providing photographic effects previously not possible without special equipment. For example, possible applications include but not limited to 3D scanning and reconstruction, shallow depth of field portraits, Dolly zoom effect, etc. The Dolly zoom effect was first conceived in Alfred Hitchcock's 1958 film Vertigo and since then, has been widely used in movies. Therefore, such effect is often referred to the vertigo effect in the filming industry. To achieve this cinematic effect, the camera is moved either forwards or backwards from the subject under focus, while simultaneously adjusting the field of view in order to maintain the size of the subject in the frame. This leads to a continuous perspective distortion, with the most directly noticeable feature being that the background appears to change size relative to the subject. The visual appearance for the viewer is that either the background suddenly grows in size with detail overwhelming the foreground, or the foreground becomes immense and dominates its previous setting, depending on the way in which the effect is executed. Executing it requires skill, practice, and equipment. It is especially difficult with a mobile camera. Previous attempts at automatically simulating this effect required the use of a specialized light field camera, or capturing images while moving the camera. This paper presents a novel technique to model this effect using camera geometry, and propose a novel synthesis pipeline to simulate the effect, given a single shot of single or multi-camera captures. Here, we define the single shot as image plus depth capture, as known as RGBD, from each camera at a particular time and location. The single shot single camera Dolly zoom synthesis pipeline is as shown in the figure. Here, the input is the image, denoted as I, with FOV theta and its depth map, denoted as D. We apply digital zoom to both I and D through inverse warping to a certain angle, say theta 1, to obtain the zoomed-in image I1 and the corresponding depth map D1. The original input image I and depth map D are reused as I2, D2 respectively. With our closed-form mapping formula, a synthesized image I1DZ and its depth D1DZ are produced from I1 and D1 through forward warping and Z buffering for a given index T in the image sequence. Similarly, a synthesized image I2DZ and its depth D2DZ are produced from I2 and D2 through forward warping and Z buffering for the given image sequence index T. Then the synthesized images I1DZ and I2DZ are fused together to form the fused image IF, while the synthesized depth maps D1DZ and D2DZ are similarly fused together to form the fused depth map DF. Then, occlusion areas in IF and DF are handled by our proposed depth-aware image in painting to obtain I bar F and D bar F. After view synthesis and occlusion handling, the shallow depth of field effect is applied to I bar F to obtain the final Dolly zoom synthesized image result. This effect involves the application of depth-aware blurring. To mimic the actual Dolly zoom effect, we also derived closed-form relationship between the size of the circle of confusion and the field of view relationship in the image sequence. The usage of shallow depth of field effect is twofold: 1. Enhanced viewer attention to the objects in focus, and 2. Hide imperfections due to image warping, image fusion and hole filling steps. For details of each block, please refer to our paper. The single camera's single shot Dolly zoom synthesis pipeline can be extended to input images captured from multiple cameras at the same time instant with minor modifications. Consider a dual camera setup, where the inputs are the image I1 with FOV theta 1, and its corresponding depth map D1 from the first camera, the image I2 with FOV theta 2, and its corresponding depth map D2, from the second camera. In this case, the application of digital zoom in single camera pipeline is no longer required. The remaining of the pipeline remains the same. Now let's take a look at some of the sample results. For example, in this single camera single shot case, I2 is the input, I1 is the digital zoom version of I2. The Dolly zoom synthesized image sequence with shallow depth of field is shown with the dog in focus. In this example we demonstrate the capability of our pipeline for dual cameras single shot case. As a conclusion, we have presented a novel modeling pipeline based on camera geometry to synthesize the Dolly zoom effect. The synthesis pipeline presented in this paper can be applied to single camera or multi-camera image captures. The focus of our future work will be on advanced occlusion handling schemes to provide synthesized images with subjectively greater image quality. Again, thank you for your interest in our paper. We also provide supplementary videos at the end of this presentation for your reference.
Okay. So thank you, Yanuan, for the video, and sorry that we were unable to connect you to the call. The speaker will be available in the QA session afterwards to discuss their work. So in the schedule now, we're due to take a break for 15 minutes. And when we return, it will be the second keynote by Raquel. So thank you everyone for joining this session, and apologies for the technical troubles that we've had.
Now we will be presenting the keynote from Raquel Urtasun. She is the chief scientist of Uber ATG and the head of Uber ATG Toronto. Also, she is an associate professor in the Department of Computer Science at the University of Toronto. And we are really glad that she has sent us this video as a part of her keynote presentation. So let's hear the video now. Thank you.
Hi everyone, my name is Raquel Urtasun and I'm the chief scientist at Uber ATG, as well as a professor at the University of Toronto. Today, I will be talking about simulation for self-driving vehicles. A critical component to making self-driving vehicles a reality is verifying their safety.
Christian, there is no
For example,
audio.
how can we properly evaluate that a self-driving vehicle will perceive and stop for attack? Hi everyone, my name is Raquel Urtasun and I'm the chief scientist at Uber ATG, as well as a professor at the University of Toronto. Today, I will be talking about simulation for self-driving vehicles. A critical component to making self-driving vehicles a reality is verifying they are safe. For example, how can we properly evaluate that a self-driving vehicle will perceive and stop for attack, an actor we might rarely see? Or how do we make sure that the SDV will stop in time if an occluded actor suddenly enters our lane? The self-driving industry uses a combination of 3 different approaches for evaluating and testing SDVs. First, there is structured testing, which tests the SDVs under a set of reproducible scenarios. This is typically done at a test track facility.
I think there is a glitch with the system.
This test setting is considered high fidelity,
second.
since we can evaluate the full autonomy system and hardware of the car in the real world on a particular scenario. We also consider this testing to be reactive. As the SDV perceives the scene and performs a maneuver, the other agents in the real world can respond to its behavior, and the sensor observations are accordingly updated. While effective, structured testing currently has some limitations. It's difficult to test extreme or dangerous situations such as high-speed avoidance maneuvers. Additionally, large-scale testing is impractical. We can also evaluate the SDV on pre-recorded real-world data. This potentially provides a more realistic setting for urban driving scenarios compared to structured testing. However, this simulation is not reactive. The sensory data and other actors' behaviors are not updated according to the SDV's actions. It is also still difficult and potentially unethical to collect and test safety-critical cases at scale. The third method is to use simulation. While simulation systems have a domain gap with the real world, simulation has some significant advantages. The agents and the environment in simulation can be reactive. Simulation allows testing any safety-critical scenario easily. And more excitingly, simulation has the potential to be scalable. Not only can we perform millions of different evaluation tests, we can also use simulation for training different autonomy algorithms. We now review the self-driving vehicle autonomy system and how we can inject simulation for evaluation. Every fraction of a second, the vehicle senses the environment. The perception system is then responsible for estimating where the objects are in the scene. The prediction system then predicts the output of perception, then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. Traditional simulators only simulate bounding boxes trajectories, enabling only motion planning evaluation. This is a typical approach in industry due to ease of running and relatively low overhead. It makes the assumption that the self-driving stack is modular and just uses active dynamics for traffic simulation. End-to-end closed-loop testing of the full autonomy system requires going farther than just simulating bounding boxes and trajectories. We need to have a complete simulation system that models the real world accurately. To build such a complete simulation system, we need to animate the dynamic state of the environment, where we have actors, including vehicles, pedestrians, and cyclists, construct geometry of both the static environment and the dynamic actors, and finally, simulate the sensor observations the SDV receives. We begin our discussion with simulating the actor dynamics, and we refer to this component as actor sim. The goal of actor sim is to generate actor behaviors that are high fidelity, realistic, in that it models human behaviors well, and diverse, in that it covers all plausible behaviors. These attributes are critical to enable the main application of this simulation system, training and testing the SDVs on unseen, rare, harmful events that can happen. Understanding and replicating human behavior is a key theme in both autonomy development and simulation. But there are key differences between the requirements in actor simulation and those in prediction and motion planning. In motion planning, the goal is to generate the safest and optimal trajectory plan. Even though we might learn by imitating human driving, we are interested in learning only the best driving behavior. Whereas in actor simulation, we are interested in recovering the full distribution of human behaviors, which includes potentially reckless maneuvers. In comparison to prediction, where we have partial and noisy observations, we might assume perfect information about the environment and other actors. This enables us to centrally coordinate actors to create scenarios if necessary. Most importantly, actor simulation is a closed-loop task, where previous plans influence future states. In other words, the underlying task is a sequential decision process, and we cannot make IID assumptions. There is a spectrum of fidelity with which we can animate the dynamic actors in the scene. At the simplest and inflexible end of the spectrum, we can manually specify fixed trajectories for each actor to follow in the scene. This is in fact how most test scenarios for SDVs are specified. At a more advanced level, actors can execute simple lane following behavior, given a fixed route to follow. But these approaches are all gross simplifications of the real world. To arrive at a model with high flexibility and fidelity, it's necessary to capture complex non-compliant behaviors, which include lane changes, cutting corners, U-turns, etc. Different styles, such as aggressive, cautious, and interaction, such as yielding and coordinating. Different use cases of the simulation system require different degree of fidelity. When evaluating SDV's reactive capability, it's often sufficient to specify fixed trajectories for actors of interest, since they do not need to react to the SDV. But when evaluating the SDV's proactive capabilities, such as merging onto a busy lane, we need to accurately model how an actor yields to the SDV. Lastly, to evaluate SDVs in general complex and symmetric scenarios without handcrafting them, we need the biggest fidelity actors to automatically generate interesting, challenging traffic flow. Most teams in the self-driving industry are still relying on traditional engineering approaches, which are limited in fidelity. Learning-based approaches have shown promise in developing high fidelity actor models, as they leverage and scale with the abundance of label data. Direct policy learning and inverse reinforcement learning are popular learning-based approaches. While there are a suite of different sensors that can be helpful on the self-driving car, such as LiDAR, camera, radar, IMU, infrared, and so on, we focus our discussion today into LiDAR and camera, as they are the sensors most prevalent in self-driving cars. Sensor simulation of LiDAR and camera data is a challenging topic. Both sensors require building a virtual representation that accurately models the geometry of the real world, and then performing realistic rendering of the scene. For realistic geometry, the field typically splits the problem into two components: background scenes, such as roads and buildings, and dynamic agents, such as vehicles or pedestrians. After building geometry, we generate sensor observations. I will now discuss LiDAR simulation for self-driving. Here we show a LiDAR sensor on one of our vehicles. There are two primary ways in the field to simulate LiDAR: graphics-based physical renderers and data-driven approaches. I will discuss both of them now. The standard graphics, such as simulation approaches based on game engines, like CarLiner, simulate LiDAR by designing 3D assets by hand, building a virtual city, and then physics rendering the LiDAR. The advantage and disadvantage of graphics-based engine simulation is explicit world and physics modeling from the ground up. This allows for total control of the world and precise definition of all the assets. But unfortunately, it is expensive to create these assets. It is not scalable to have virtual worlds for the numerous cities we want to test, and the simulated LiDAR is also unrealistic typically. One reason why the previous LiDAR simulators are unrealistic is that game engine simulators use low-poly assets to speed up sensor sim, and don't properly model LiDAR physics, such as material reflectance properties or the specific calibrations of different LiDAR sensors. Blender attempts to model this with enhanced graphics modeling of physics and calibration. Unfortunately, enhanced graphics suffers more so from the issue mentioned earlier, with the additional disadvantage that simulation is slow. They report a single LiDAR shape takes 8 to 9 seconds per frame to generate, preventing scalable autonomy testing. Data-driven approaches, instead, show how we can use sensor data collected from the real world to build 3D assets, and then apply rendering to simulate the LiDAR. This recent work shows off-road terrain LiDAR simulation by generating assets of vegetation and road. It will be very desirable to have a similar approach for LiDAR simulation in the urban driving environment that we are interested in. That is what AADS LiDAR simulation does from the Vertigo Apollo research group. They use a high-end LiDAR scanner to collect highly accurate background scenes, which they combine with a collection of CAD models and probabilistic scene generation to generate LiDAR sweeps. This approach is promising, but is still constrained in scaling due to the set of CAD models that it requires in order to create the simulations and the use of an expensive scanner over $1 million to create the virtual world. It also does not fully model all the physical effects of the LiDAR, such as the rolling shutter and motion blur of the actors. Our work, which will appear at CVPR this year, is called LiDAR Sim, and builds on the past work by incorporating both graphics and data-driven approaches, along with machine learning. LiDAR Sim builds assets at scale using a fleet of self-driving cars with standard sensors, and then uses physics with machine learning to generate realistic LiDAR simulations at scale. I will not discuss in more details the different components of LiDAR Sim. LiDAR Sim leverages millions of real-world mice collected by our fleet of self-driving cars to help build virtual rules for autonomous vehicle testing. On the right, you can see the reconstructed background scenes of an intersection and a collection of the different dynamic objects created from LiDAR data. Here we show how LiDAR Sim generates realistic backgrounds. We record real LiDAR data by driving in an area and remove moving objects using automatic 3D semantic segmentation. We aggregate and align the LiDAR, combine across multiple trajectories, and create a mesh-solve for representation of the background. A similar process is done to generate dynamic objects. We utilize a symmetric prior to get a complete shape of the object. Leveraging real data allows us to inject the diversity of objects seen in the real world into LiDAR Sim. From left to right, we can see cars with open hood or trunk, bicycles on top of the car, flatbed trucks with construction cones, and trailers with extended cars. Making sure we can detect these rare objects as vehicles is important, and by leveraging real data, we can simulate more situations that are in the long tail. You often don't see the diversity of these 3D assets on CAD model datasets. Once we generate our assets, we can place them in a scene configuration, just like in a video game. We now have scalable and diverse scenes. We then perform realistic sensor simulation with a combination of physics and machine learning. LiDAR generates point clouds by shooting light into the scene and measuring the travel time to determine an object's distance. To mimic this process, we recast our scene and generate a simulated point cloud. However, raycasting generates more returns than real LiDAR, since the return light does not always meet the detection threshold. We call this phenomenon ray drop. Ray drop is complicated to simulate by physics alone, because we don't know the physical parameters of the real world. Fortunately, using a ray drop network will leverage real-world data and ML to bridge the scene-to-real gap. We convert this LiDAR sweep into a spherical image representation, encoding features related to ray drop, such as range values, incident angle, semantics, and path intensity values. We then feed these features into the network and predict how likely a ray will be dropped. The labels come from real LiDAR ray drop patterns. We sample the ray drop probability to generate the final point cloud. We now show results. Green boxes here indicate vehicle detections from a model trained on real data only. This side-by-side comparison shows that LiDAR Sim generates realistic point clouds with a small domain gap for downstream perception tasks and autonomy testing. We now compare LiDAR Sim against Carla, a state-of-the-art sensor simulator. A model trained with Carla data and tested on real data has a large sim-to-real domain gap, but a model trained with LiDAR Sim has just a 1% domain gap, significantly outperforming Carla. The small domain gap means LiDAR Sim is effective for data augmentation. By combining LiDAR Sim data with real data, we gain a significant performance boost for vehicle detection with both small and large amounts of real data. LiDAR Sim also allows us to evaluate a perception and motion planning system maneuvering safety-critical scenarios in a closed-loop setting. Here we see a simulated scenario where a vehicle turns into the SDV's lane, occluded by a bus. The system, trained only on real LiDAR data, is able to process LiDAR Sim data and safely brake to avoid collision. With no additional training or domain adaptation, we can directly use LiDAR Sim to test an autonomous system end-to-end on millions of different scenario variations, achieving results that match closely with the real world and allowing us to gain new insights. Along with LiDAR, the camera sensor is another critical component for most self-driving autonomous systems. So we are going to now turn our attention to camera simulation. Modern autonomous driving car platforms are equipped with multiple high-resolution cameras, covering different viewpoints. For example, front view, side view, and rear view. This requires us to simulate camera images which are consistent across viewpoints and time. I will first review graphics-based camera simulation and recent progress in using neural networks for camera sensor simulation. I will then present 2 recent efforts towards photorealistic camera simulation at this scale from the lab, which are shown today for the first time. Graphics-based camera simulation relies on classic rendering techniques. On one hand, real-time rendering is cheap and efficient, but does not produce photorealistic sensor data. On the other hand, high-fidelity rendering is very expensive and hence not scalable, as it usually takes a few hours to render a single image. Recent neural rendering methods formulate the camera sensor simulation as the problem of conditioned image generation through semantic layout to image translation, domain adaptation, and image manipulation. However, these single view-based methods cannot be directly applied to create the virtual environment for self-driving cars, as the simulated camera images are usually geometrically inconsistent. Other methods insert 3D vehicles into the scene by encoding and manipulating semantic image representations, or manually specifying vehicles in new locations and rendering them. However, this requires very expensive manual editing and hence is not scalable. In addition, these approaches do not have a 3D scene representation, making them difficult to extend to video or for handling interactions with other actors in the scene. In contrast, I will present now 2 novel efforts towards photorealistic camera simulation by leveraging existing camera sensor data and the 3D geometry of the scene. First, we study the problem of dynamic object removal from the 3D scene. The output of such a process can be used as a blank state for adding virtual dynamic objects. Second, we study an inverse problem, namely, inserting dynamic objects into the scene in a geometrically consistent and physically plausible manner. As we automate camera simulation in both efforts, we can create a great amount of scenarios that potentially capture the diversity in the long-tail distribution of driving data. So let's go over the first work. Given a sequential multi-sensor data in the form of multi-view camera images and sparse later point clouds as input, we design a smart 3D editing program that is capable of removing all dynamic objects, for example, vehicles and pedestrians, in the scene and recovering background structures such as buildings, road, vegetation, and sidewalks. Towards this goal, we first reconstruct the 3D geometry of the scene and then propose a data-driven approach based on the reconstructed geometry. Core to our system is a novel geometric-aware in-painting network that learns to remove dynamic objects from the 3D scene. The proposed network works in a coarse-to-fine manner. The coarse network learns to make the initial predictions of the image, depth, and semantic layout on the region to be in-painted, while the refinement network learns to generate detailed textures from those predictions. We refer to the initial predictions from the coarse network as the intermediate multimodal representations. To enhance the perceptual consistency over time, we introduce an additional temporal feedback. Given 2 frames, the predicted output at frame 1 is reprojected to frame 2 and passed back into the generator for in-painting the second frame. Our temporal feedback is built into the model itself and is trained end-to-end with the rest of the network. Finally, we introduce a novel geometry-aware temporal attention model that copies and borrows features from the visible regions in other frames to the target regions to be in-painted. Since our approach is efficient, we can exploit a large temporal window. This is achieved by computing the feature similarity between the pixels to be in-painted and the spatiotemporal tube on the reprojected images centered around the corresponding pixels. This is efficient as it requires only a minimal number of candidate patches during training and can also dynamically scale to make use of more or fewer views depending on the computational resources. In this video, we provide a side-by-side visualization of the inputs. Of the input video, the output from the proposed method, as well as results from 2 state-of-the-art video and painting algorithms. Our approach generates more photorealistic and geometrically consistent results as we leverage the 3D geometry explicitly through our network design. In contrast to existing video in painting works, we take advantage of the geometric correspondences with longer time horizons, which really helps our approach. We now show the opposite problem, which is inserting dynamic objects into an existing video sequence and generating a photorealistic video of the augmented scene. So let's go over it. Let's start with a question. Which of the objects in the depicted images are fake? Let me give you a few seconds. Did you guess correct? What Yaser is using a novel approach that leverages active sim as well as 3D geometry of the scene to simulate camera sensor data from multiple viewpoints which are geometrically consistent. GeoSim takes advantage of recorded camera data, data sweeps, and 3D bounding box annotations to aggregate real-world sensor data for dynamic objects encountered in the wild. Such data is readily available in modern self-driving datasets. With our approach, we can generate a large-scale and diverse 3D object bank with precise geometry, high-definition appearance, and accurate 3D poses. To build our assets, we develop a 3D reconstruction network that takes camera and LiDAR sensor input from multiple viewpoints for a given dynamic object and outputs a high-precision 3D shape. Specifically, we process and combine crop LiDAR point clouds and images into a single feature embedding, which we then use to predict the formations to a min template shape prior. We then perform energy optimization on the predicted shape to make sure it agrees with the input LiDAR and images. Note that we don't require any ground truth 3D shape data. Here are some examples of 3D assets which we reconstruct with our approach, as well as the corresponding images. Note that we can model vehicles of different sizes and shapes. We then place 3D assets onto the high-definition map so that they reflect the traffic and 3D layout in a realistic manner. Note that our object placement is not only 3D aware, but is physically plausible and temporally consistent. We leverage an intelligent driving model for simulating the vehicle's trajectories over time and making sure it has realistic acceleration and braking such that the full scenario is coherent and realistic. We use a novel view rendering with 3D occlusion reasoning with respect to all elements in the scene to create the appearance of the novel object in the new camera image. We finally generate photorealistic camera simulation using a post-completion image synthesis network, as depicted here in the image. Unlike existing work on neural image synthesis and manipulation, which either requires human interaction, is not realistic, or only models the 2D context, our approach is fully automatic, photorealistic, and 3D layout aware. We compare the proposed GeoSim with the state-of-the-art 2D neural rendering methods, as well as a retrieval-based copy-paste baseline. Compared to 2D-aware image generation models such as Pix2Pix HD or guided editing, GeoSim produces much more realistic augmented images with little to no distortions or aberrations. And compared to a single copy-paste baseline, we can see the value of GeoSim's 3D-aware placement and occlusion reasoning for a reasonable image scene, along with in-painting to remove boundary effects that otherwise would be visible. We also measure the perceptual realism of the simulated images using A5D. Our method is capable of producing significantly better quality images than the state-of-the-art. To further verify the realism of GeoSim, we conducted a human A/B test. We show a pair of images generated from different approaches on the same background real image, one from GeoSim and another one from a competing algorithm to the users. We then ask the human judges to click the one they believe is more realistic. From over 20 users and close to 5,000 images, we can see that GeoSim images are preferred more than 94% of the time, and with respect to some of the baselines, even 99% of the time. This confirms that there is a significant gap between other baselines and GeoSim that is immediately noticeable to humans. In addition, we conduct downstream perception tasks, including image segmentation, 2D object detection, and monocular 3D object detection on the simulated images and compare the performance with real images. We now show how perception algorithms trained on real data perform on images generated from the different simulation baselines. We first show the results on real images. The numbers in the parentheses indicate the performance gain or loss using different simulations. Here are the results of the different image generation baselines on the different tasks. We want to emphasize here that a higher IP or mean IOU perception metrics or on simulated data is not necessarily better. Instead, we want the perception metrics to closely match the perception on real data. This difference is reported in the parentheses. The closer the metric on simulated images matches with real, the more likely the perception algorithm considers the simulated image as being from the same distribution as the real data. As we see in the table, there is a clear difference between using real images and synthetic images generated by 2D based neural painting methods. In contrast, the proposed GeoSim not only produce visually plausible images, but also the perception algorithm is trained on real data alone will generate consistent results reflecting the correct semantics in both GeoSim and real data. Let's go over qualitative results. Here is an example of a scene with a simulated object. Can you tell which one is the simulated? Notice that we can simulate objects at different and diverse viewpoints, front or back, close or far away. We can accurately handle occlusions with static background objects, other vehicles, and even pedestrians. Even more exactly, we can extend our geometry-aware image simulation by composition approach to video simulation. Notice that our simulated images are temporally coherent and that the added objects obey traffic and have reasonable motion. Multiple objects can be added to the scene and interact with each other, for example, performing lane changes. Being 3D aware also means we can also do multi-camera simulation that is physically possible. In this case, this will be two cameras mounted in different locations in the self-driving car, how they will perceive the scene. We hope GeoSim is the next step in providing realistic camera simulation for autonomy testing. Thank you. In summary, full autonomy testing and training means we need to have multiple components. To build such a complete simulation system, we need to animate the dynamic state of the environment, where we have actors including vehicle, pedestrians, and cyclists, construct geometry of both the static environment and the dynamic actors, and finally simulate the sensor observations the SDV receives. We're excited about simulation. There is a lot of exciting areas for the community to explore. Simulating all kinds of sensors, building the world, and automating the training and testing of what matters most. Thanks for listening. Hi, everyone.
Hi, everyone. So that was the talk by Raquel, an amazing talk by Raquel. And unfortunately, she couldn't join us for question and answers because she's doing a tutorial at CVPR again. But what we have done is we have arranged a live presentation from Yangwen Ling, who wasn't able to do it in the previous session because of technical glitch. So I will ask Yangwen to take over now. Yangwen, if you're ready. You can share your screen.
Okay. Okay, great. Thank you.
And you have until 35 past the hour because we start our panel discussion then. Yeah?
Okay, sure. Can you see my screen now?
Yes. So.
Okay, cool. Hello everyone. Thank you for your interest in our paper with title Vertigo Effect on Your Smartphone, the origin via single-shot view synthesis. My name is Yang Wen Liang. I'm from Samsung SOC, San Diego, California. So these days, camera on a smartphone are more sophisticated than they have ever been. Mobile phones now come equipped with multiple camera of different modalities. A typical setup may include 2 or more cameras with different focal lengths, providing different field of views. And then, in addition, a dedicated depth camera or sensor to provide long-range, high-accurate depth information within the scene is also very common. Such setup make user photography to next new levels and open up possibility of providing photographic effects previously not possible without special equipment. For example, possible applications include but not limited to 3D scanning and reconstruction, shallow depth of field portraits, and Dolly effect, and so on. So the Dolly effect was first conceived in Alfred Hitchcock's 1958 film Vertigo, and since then it has been widely used in movies. Therefore, such effect is often referred to as the vertigo effect in the filming industry. To achieve this cinematic effect, the camera is moved either forward or backward from the subject under focus, while simultaneously adjust the field of view in order to maintain the size of the object in the scene. This leads to a continuous perspective distortion, with the most direct noticeable features being that the background appears to change size relative to the subject. So, for example, in A, the camera is at position 1 with a focal field of view theta 1, where the yellow object under focus. And in B, the camera move to position 2 while increase its field of view to theta 2. After the camera movement, the size of the yellow object remain the same, while the size of the background object appear to shrink, while more objects are brought into the image due to increase in field of view. And C shows the illustration of the effect where the camera is moving in the opposite direction, that is pulling away from the object. So as the illustration shows, the visual appearance for the viewer is that either the background suddenly grow in size with detail overwhelming the foreground, or the foreground become immense and dominate its previous setting, depending on the way in which the effect is executed. Executing the origin effect takes skills, practice, and equipment, so it's not easily for the mobile phone to achieve such effect. So previous attempt at automatically simulating this effect requires the use of specialized live field camera or capturing the image while moving the camera. So our proposal presents a novel technique to model this effect using camera geometry and propose a novel synthesis pipeline to simulate the effect. Given a single shot or multi-camera capture, here we define the single shot as image plus depth capture, as known as the RGBD capture for each camera at a particular time and location. This single shot, single camera Dolly synthesized pipeline is shown in the figure. So here, the input is from the single camera, and the input is the image I with field of view theta, and its depth map denoted as D. And then we apply a digital zoom to both the image I and D to generate to use inverse swapping to certain angles, say theta1, to obtain the zooming image I1 and the corresponding depth map D1. The original input image I and D are reused as I2 and D2 respectively. So with closed-form mapping formula, synthesize image I1 DZ and its depth D1 DZ are produced from I1 and D1 through forward warping and Z buffering for a given index for a given camera movement in the image sequence. So in such case, we are able to generate the new synthesis view of the camera. So after that, similarly applied to the I2 and D2, we will generate a new synthesis view of I2 DZ and D2 DZ. So with these two image sets, we are able to do a image fusion to fill out the holes within the some of the holes within the fusion images. So in this case, with fusion image I1 DZ and then I2 DZ. In such case, we can see that some of the border has been filling with the with some pixels coming from the I2 DZ. And similarly, the depth map can do the same thing to fill in the filling some of the occlusion and missing area. So with that, then after that, we need to do a in order to handle the occlusions for each synthesized Dolly view, we identify occlusion areas and filling them by our proposed depth-aware image in painting for satisfactory subject viewing. In this case, we first do the occlusion handling on the depth map. And later then, with the depth map, we are able to do a depth-aware image in painting to fill the final images. And then after that, the shallow depth of field is applied to the Fi bar to obtain the final Dolly synthesized image output. This effect involves the application of the depth-aware bearing for mimic the actual Dolly effect. We also derive the closed-form relationship between the size of the circle of confusion and the field of view relationship in the image sequence. The use of the shallow depth of field effect is twofold. One is to enhance the viewer attention to the object in focus, and two is to hide the imperfection due to image warping, image fusion, and hole filling steps. So for detail of each block, please refer to our paper. So the single camera, single shot Dolly synthesized pipeline can be extended to input image capture from multiple camera at the same time instant with minor modifications. So we consider dual camera setup. In this case, the input are the image I1 with FOV of theta 1 and its corresponding depth map D1 from the first camera, and the image 2 and with FOV theta 2 and its corresponding depth map D2 from the second camera. So in this case, the application of digital zoom in single camera pipeline is no longer required. The remaining of the pipeline remains the same. So now let's take a look at some of the sample setups. So we generate a synthesized image data set using the commercially available graphics software Unity 3D. For the example, we assume a dual camera system. Camera 1 with a focal length of field of view of 45 degree and camera 2 with a field of view of 77 degree. So in addition, each image set also include the ground truth story zone view, which are also generated with the Unity 3D for objective comparisons. So we objectively measure the quality of the view synthesis by computing the PSNR and the SSIM. For each synthesized view against the corresponding ground truth image at each increment after the application of the shallow depth of field effect is also shown. So as we can see that as the Dolly angle increases, the area of image that needs to be inpainted due to occlusion increases, which corresponding to the drop in the PSNR and SSIM. So and then this is some of the videos, and this one of the video with SDOF, and this is another image set with a different person. And we also, because we got the ground truth in the synthetic data set, and then we are able to calculate the PSNR and SSIM. So now, for example, in this case, we also show some real image captures. So in this case, it's for the single camera smartphone case. I2 is the original image, and I1 is the digital zoom of it, and then the result is given as the with the shallow depth of field. And for another case,
Yangwen, we have run out of time, so because we have to start a panel session at 35 past this hour.
Okay, yeah, that's it. Yeah, that's pretty much it for the examples. And yeah, as a conclusion, basically everything is in the paper. Thank you.
So I would like to thank Yangwen for his presentation. Now it's time for panel session, and I would ask Dan to take over, please. Thank you.
Thank you.
All right. Okay, so welcome everybody. So this is going to be our last session of this workshop, which we have prepared a panel discussion that's going to be among the presenters and the organizers. So let me see if we arrange the visualization properly. And if all the participants can enable their microphone and camera, please. All right. Okay, so we're gonna start this panel discussion with a quick introduction with all the panelists. I start off, and then we'll follow maybe first the organizers, then Keynote, and finally the paper presenters. So my name is Dan Casas. I am assistant professor at the University Rey Juan Carlos in Madrid, and I am interested in mostly 3D reconstruction of avatars, lately a lot related to clothing, trying to model how the surface of avatars and clothing deforms. Armin, maybe you want to introduce yourself? Yeah, remember to unmute yourself when you introduce.
So my name is Armin Mustafa. I am RAN's research fellow at University of Surrey. And I mainly work in dynamic scene reconstruction, focusing on people. So that's my research area of interest.
Maybe Michael, you want to go ahead?
Sure. I'm Michael Solifer. I work in Pittsburgh at Facebook Reality Labs, and I'm currently really interested in all kinds of neural rendering approaches for generating synthetic images of real scenes.
So we also have Christian as the organizer, Christian Richard. Maybe it's actually, sorry, maybe Christian is busy. Yeah, I know Christian is managing all the audio and video tools. So maybe we can jump to Marco, which is also a co-organizer, Marco Bolino.
Yeah, thank you, Dan. Yeah, my name is Marco Bolino. I'm a research fellow at the University of Surrey Centre for Vision, Speech and Signal Processing. And my research interests are in volumetric video and how to utilize it for VR and AR applications.
Thank you, Marco. So we have Yaser here, Yaser Sheikh. He gave a keynote earlier this morning. Hi, Yaser. Yeah, and then I think we have all the paper presenters in the end. We managed. We have Sinet, Marcus, Yang Wen, and Zhong Pai. Okay, thank you guys. You already presented yourself on your talks. So, so the idea here is that I'm going to pose a few questions around dynamic scene reconstruction, which is the main topic of the workshop, and then we can discuss a little bit our ideas and our thoughts about these questions or topics that I will highlight. Right. So I wanted to start off by something that actually I thought when we got the submissions for this workshop, the workshop is called a Dynamic Scene Reconstruction, but then I realized that we hardly had any submission for like purely general dynamic scene reconstruction. Then what happens is that you say we accept submissions for dynamic scene reconstruction, and we end up getting somebody doing faces, somebody doing dogs, somebody doing humans, etc. Right? So then I was wondering how far. I mean, it's true that in CVPR in general and in the state of the art in general, there's some works that address a more general dynamic scene reconstruction, but in reality, then people focus on a specific domain mostly. So I was wondering, what are your thoughts? Maybe I'm interested in listening to Yaser, which you have a lot of experience in that, and lately he's focusing in humans, right? So I know you said you're going to target each specific area of humans, but in the end, it's just humans because you're interested now in this social interaction, right? But that is still a sub-domain of our world, right? Our world is dynamic, and everything moves, and we have all sorts of objects and scenes, right? So how far are we from, ideally, I want a codec avatar, but for any scene, right? that's what I want, right? So why is this not happening yet, and how far are we from this happening?
Right. Thank you. I think it's an excellent question, and you're actually right that it's a problem which is very sort of close and dear to my heart. In fact, when I joined this faculty at CMU, it was the first area of research that I really wanted to attack and tackle, there was multi-view geometry was sort of, I mean, of course, there's still active research, but as a field, it was coming to a close because a lot of the core principles were learned and known, and there were some excellent books out there. And it was the problem of trying to simultaneously figure out, camera positions as well as static 3D structure. And I thought it was a very good next step would be to see if we could get dynamic scenes with cameras as well. After about a decade of research, my conclusion on this topic is that it is too severely under-constrained. Like, if you think about the core problem of trying to reconstruct a general scene from free camera movement, the scene is moving, the camera is moving, for any scene. You had to sort of like contend with not just cameras and scene structure, but camera, model building, because there had to be some regularity in the types of movement, as well as then the parameters of that model as well. You had to simultaneously estimate these three quantities from a single monocular view. And it turned out this was too severely under-constrained. We had some results. There were a couple of other groups at ANU and in Italy as well. We kept on showing results, but these systems tended to be extremely fragile. They would work with very sort of like a severe movement, or when the movement of the scene sort of interfered with the movements of the cameras, it would only work or demonstrate some robustness in those cases. So more and more it was apparent that because this problem is so inherently under-constrained, we had to use some sort of knowledge about the scene, right? And I think you're very right that, obviously the first thing to do is narrow the domain and try to demonstrate it's working. But it really lends itself an opportunity to revisit these problems now that we have much larger data sets, we have much more powerful, dynamical modeling systems in deep networks, to see whether we can revisit the original problem like a single view with a lot of prior data. Can we start to do reconstructions of the camera, the model, as well as the parameterization? And maybe it'll see a comeback. But the reason why I moved out, and I suspect many people moved out, is that the ambiguity was too large. It was too under-constrained as a problem.
Mm-hmm. Yeah, thank you for your thoughts. I don't know if any of the other panelists has experience in trying to address more dynamic. I know Armin had some interesting works on more general dynamics, 3D reconstruction. Well, it's still constraining up to some domain, but you, Armin, had at least without any prior in geometry, which is already a step forward, right?
Yeah, so I mean,
so you, Armin, and Michael are also asking for some. So
yeah.
Please, Armin and Michael.
Yeah, so I think my work mainly focused on humans again, but the idea was to not use any priors and achieve a reliable reconstruction. But I was doing all that from multiple views, and my current work is focusing on achieving the same sort of reconstruction without any priors from single view. And what I've noticed is that when you combine different views together, it helps. For example, I've tried to use semantic segmentation within the reconstruction framework. I've tried to use motion information, which I think helps in overcoming the amount of priors you need to get the reconstruction. So this is my Michael, you can go ahead.
Yeah, I just wanted to add one or two things. I totally agree. I think it's a really tough problem, especially if we think of like a single RGB camera, to get like, where is the camera and like, how is the geometry moving and so on. What I was actually surprised is that we didn't get a lot of submissions which leveraged RGBD sensors, for example, because there has been a lot of really great work on that, like a few years ago, if I think of dynamic fusion, for example. But these approaches are all these classical optimization-based approaches still, that try to kind of like fuse a volumetric model and then in an optimization-based way register it against these new depth observations. I think why we don't see a lot of that right now is maybe also lack of data for general objects. I guess this goes in the direction what Yaser said. Like for faces and hands and bodies, we have a lot of data. And we've built all these like these more low-level tracking primitives, like we have key point detectors, which help a lot, and so on, which we're missing for general dynamic objects right now. They are not that sophisticated. But I think if we would go to a single RGBD camera, there would be a lot that we can even do with deep learning for general non-rigid reconstruction of dynamic scenes.
Yeah, I guess there's always the question about what modality or sensitivity input is the one that you want to target, right? Because in the end, if you want to go to the market and there is no RGBD sensors available, then you're doing a work that it's not too useful, right? So I guess that's also a question, no? There's always this, for self-driving car, there was also this question whether you assume you have LiDAR or you don't have LiDAR, right? So there's always this modality input that that somehow conditions or at least try to drive the approaches you want to work for. So regarding the general scenes, what I do see in the latest, maybe the last 2 or 3 years, some improvements on depth estimation for general scenes. I think this is starting to work out pretty well, at least in learning-based methods. I've seen some papers where they are able to estimate the depth in the wild setting. Usually, the first papers were more about indoors, rooms, etc. But maybe self-driving cars too, because you always assume like, there's a road and there's a stuff that is more or less constrained. But I think there's more and more work in at least estimating the depth, which is a first, information you can estimate from a general scene. Of course, depth is just depth. Then you need to put some geometry there. Then you need some instantiation and segmentation, etc. But maybe it's a first step towards a more general setting. I don't know if you guys have experience with general depth or if you have a comment about that.
I think generally one of the interesting sort of questions, really it's about, especially when you want to do reconstructions, it's about correspondence. I want to second the point Michael just raised about establishing correspondence. One of the things was the 3D reconstruction really became industrialized once SIFT was proposed, right? That was the linchpin. That was the breakthrough. The theory was known for a while, but that was really the crux of it. And we, of course, all of us who work in this area know that SIFT actually doesn't work as well with things under deformation. Even small local deformations cause it to fail. And I really do think that there's a opportunity for learning-based methods to. Learning-based methods didn't have that much of a scope to improve SIFT because, of course, it's so good already. But there is a real scope to define something like the deformable version of SIFT. There have been a number of attempts to it, but nothing's really learned it to the extent that you could really rely on it as a component like we could rely on SIFT. And Takeo Kanade used to say, like a famous quote of his was that the 3 most important problems in computer vision are registration. And I think it's really key over here, right? If we can get something like that through learning, I think that's also the ticket. That's general, that can give you correspondences for deforming objects. That'll really, I think, spur progress. So if anyone is thinking about a problem, I think the data is out there. I think the methods are out there. It's just a question of innovating and figuring out how to actually propose that piece.
Yeah, thank you, Yaser. I think Armin had some thoughts about that.
I was just saying about monocular depth estimation. I was saying that although the methods have progressed quite well in the past few years, but still they are not generalizable. So for example, if you train a method on an indoor data set or an outdoor data set, will only work on that kind of domain and not like it, and it cannot be trained on like multiple data sets together, which is still, I think, quite a big constraint in monocular depth estimation. So that's all I want to mention.
Thank you. Yes, we had some other topics we wanted to discuss. Maybe also related to the domains that we tackled in dynamic scene reconstruction. I think it's clear that we need some benchmarks. No, I think some areas of research have very well-established benchmark, optical flow estimation or image classifications, etc. They have very well-established benchmarks, while in dynamic scene reconstructions, we don't have, or at least I'm not aware of a super well-known benchmark. No, I wonder what are the steps towards getting these benchmarks available. If we need like a big company like Facebook to do a benchmarking on 3D reconstruction of avatars, or and then how would you benchmark a super general scene, right? I think benchmarking is also important for a general dynamic scene, which we already agreed that it's a too hard problem, right? But still, maybe someone needs to put out a benchmark there just to run methods, even if they are not too good. So how about building a benchmark for dynamic scenes? What would this contain, and etc.?
Yeah, I think there were some attempts at doing this. I remember, I believe out of Michael Black's group, there was a simulation-based data set. I forget the name of it, started with S. It was
Sintel dataset, right?
Sintel? Right. Yeah, that was the right one. That was there. I feel like the real challenge in getting ground truth is there is no proxy sensor. There is no other device in existence that can give you corresponded reconstructions of dynamic scenes, except if you use multiple sort of cameras. So the rig that you would need to take to the wild to try to get that would be kind of like highly complex to get. And even then, it's not really ground truth because it's going to be inference based. So there's no like equivalent to a LiDAR or a depth camera or something that can you can use as an independent benchmarking, similar to the static case. So I really feel like that's one of the core challenges. But perhaps you can envision kind of like multiple camera systems and using those to get some sort of correspondent ground truth. As far as the avatars go, we are sort of like planning to release data sets for this to allow benchmarking, but also to encourage further work on it. The challenge is oftentimes the quantity of data that we would need to produce, because this is not just a static point cloud. It's kind of a static point cloud that's high resolution per frame. So even if we made the data available, even if we did have benchmarks, making it accessible from the computational perspective, this might be a new flavor of problems for the dynamic scene case too.
Okay. Any other thoughts about benchmarking? I know for example, you've seen it. You now released your doc data set, which might be useful. So there's attempts here and there, right? But
yeah, so part of the problem with trying to estimate pose for animals is that there was no 3D data set available where we could evaluate results. So it's part of the reason why we released the data set that we did, that we provide that information that people can then compare the results with.
Okay. So we have more questions here. Also, people watching on YouTube, feel free to write questions on the YouTube chat. We will try to gather some of them. So there's actually a question related to another question we had internally, the organizers, which is about the requirements for these data sets that Yaser was just talking, right? So we've seen the great work from Facebook and this codec avatars work, but then when I saw this picture about the light stage, improved light stage that you guys have, I was like, whoa, what's going on here, right? So like a zillion cameras there. So we see a huge gap between what a strong group and a strong company can do with average people can do. I'm talking about average research groups. I'm not even talking about individuals that are not good in research, right? Or they are not technical. So we see a massive gap there. So how do we approach this gap? How do we approach the gap between like top, super top researchers with a lot of funding, researchers with regular funding, and just regular users, right? Because then we have another question in YouTube, which is related to that, which is how do we bridge this gap between what researchers are doing and how they are doing and the consumer level? No, so I think there's still some a massive gap there.
Yeah, I think it's a very fair point, particularly since, like the cornerstone of scientific investigation is reproducibility. And if, if the cost of reproducibility is something no one except one or two groups can do, then it just excludes people from research as well. I feel very strongly about this. One of the things I did with our group at CMU is we did, in fact, open like a large data set from the Panoptic Studio there, and it is actually available right now. Multiple views, lots and lots of activities with pose, with depth. And in fact, speaking of benchmark, that shameless plug, that might be a good one. But beyond that, the Panoptic Studio still didn't have the resolution in time or in space the way we have it with our current data sets. And we are all in our lab, at least, quite committed to sharing it for this reason. As you might imagine, there are some kind of like legal and logistical constraints that we want to fulfill. But the plan is to see if we can open source all of the data that we're capturing as well. And surprisingly, there is actually a lot of support within the company to do this. So I will sort of underline it as something which I believe is our responsibility to the community. Mm-hmm. And we will see. I hope you will see in the next year or two that we will start to release a lot of the data, but also in a way which is accessible for people to use. So it doesn't help you if I give you like 10 petabytes of data if you don't have the capacity to actually ingest it and use it in some reasonable way, in reasonable amount of time.
Yeah, and I understand that you need to spend actually your own budget to properly make the data available, right? To write a nice website with a nice pre-visualization of the clips, etc., etc. But yeah, the Panoptic CMU is cool. I mean, I've played a little bit with it, so it's quite cool. I think this also goes into a direction like we have research, we have like groups with a lot of funding, with a little bit of funding. But then when I tell my mother what I work on, she can ask me, well, when I'm going to see that? When I'm going to see that? Like, when is it useful, right? Why is general dynamic scene reconstruction useful? Like, we as researchers, I see a teaser of a paper and sometimes I already get excited. Whoa, how does it work, right? But then like 99% of the world population doesn't care about that. So how far are we from? I understand from Facebook you're pushing hard towards the social media applications of what you guys are doing, but maybe we want to think about farther than just the social thing. No, like how is the concept of dynamic scene reconstruction useful to everybody, not just as I chat within the Facebook app, right?
Right.
How can we make people aware of that? Maybe, yeah.
Yeah, it's a good question. I think the possible applications of this, beyond talking to one another, though I do believe that kind of what we're doing right now, the only thing that billions of people do, there are a few things that billions of people do. One of them is chat, talking, communication. So it's a pretty hefty thing. But beyond that, the next level, which is I think what you're asking about, there are things like teleeducation, right? Right now, despite the big hype around MOOCs, they made an impact, but they didn't replace schools or universities. And part of the reason is the same question of it's very different to be taught in person as opposed to, and with your friends and peers, as opposed to doing it in isolation. So in education, I think there's a whole host of applications. Then in telemedicine, I think this is an important one because the expertise to treat people for, let's say, mental health issues, they tend to be concentrated in city centers. But patients are everywhere. They're in rural areas. They're in suburbs, in inner cities. But that's not. Maybe there's a mismatch between expertise and patients. So I think
but somehow what you're talking about applications, right? But for me, it's hard to believe that my doctor will check out something I'm feeling through my avatar, for example. Like honestly, this is like, I don't know, how far are we from that, right? Like I think we should talk about things that people we can convince people that they will have it on, like, and that it be useful for them.
Yeah, so I
applications are clear.
Probably you're right about the fact that, let's say, skin rashes and bulges, that might be a little far off. But I do think kind of like psychotherapy, that's not something that's too far off. Physical therapy, that's not something that's too far off, right? Are you walking properly? If you have your therapy sessions where the person is in front of you, I don't think that's too far off. Sports was the third one I was about to give you. That's another kind of like analysis of sorts. We already have started to see some of that. Entertainment is another one, like not just the production of it, not just the consumption of it, but even the production of it, like making it easier for an individual to produce kind of what would only have been possible with a studio maybe a few years ago. I think these are all within the horizon. The problem is, when we say they're on the horizon, usually we mean they're kind of like 1 or 2 research results away at least, which means it's very hard to predict. Is it 2 years away or is it 25 years away?
Yeah.
Because they're open. But that's the deal, right? That's the fun of doing research, is that you don't know that. And I think all of us probably have a personality type that we don't really care about it all that much. We of course care about it, but it doesn't sort of like disturb us that we won't see something ship, say, in 6 months.
Yeah, I agree. Yeah. I'm sorry, I'm talking too much to Yaser. Maybe we should open the questions to everybody else. I don't know if you guys have experience or thoughts about, making your own research available, and if you have encountered any problem in sharing your data, or trying to build data benchmarking, or you see your dog being reconstructed completely in the wild in the next 2 years or something, or your face. No thoughts about dogs or face?
Okay, so I wanted to add something. So the first thing which we were discussing about the difference between the industry and academia, I think Yaser made a very good point that I like providing the data sets to general public, like the small groups and stuff like that. That is going to help a lot. And even the Panoptic Studio was one step towards it. And in addition to that, like a lot more people are providing their codes now, which makes it easy for a new researcher to pick up those codes and then use them in their own research and probably develop something on top of it. So that makes it a little bit easier. That's what I wanted to add for that point. And I just wanted to open this. So when we're talking about data sets, right? Maybe we should think about like the difference between the real and synthetic data sets, because a lot of people are now creating synthetic data. For example, the multi-view data sets, and they are like temporally coherent meshes. So they are already registered, but training on those synthetic data sets is not the proper solution if you want to use those algorithms in like real world. So maybe what to do next? I don't have an answer for this, but this is a question which I have myself, like how to map that gap between synthetic and real world data. So I think also Michael, who raised his hand a few minutes ago, I think he wanted to add something. So maybe.
I mean, I wanted to actually piggyback on something you said in the beginning, and on all this, like, oh, we could share the data. I think actually, like, it's two things. Like, it's not only about sharing the data and making it public. Yaser already mentioned, like, people have to be able to download that data to even store it. But even beyond that, like, people need the compute to actually train a network on top of that data. And I see that as a really major challenge, and like one of the big differences between maybe industry and academia. There are well-funded like labs in academia that have the compute, but even there it's tough before deadlines from my experience. Like the cluster is full and everybody's battling for GPUs, and they are happy if they can get one or two, which just means the number of tests they can run. The number of tests you can run is just a measure of how much fast you can make progress up to a certain point. So I can see that that's a major challenge. Like if you're at a really small university, you maybe have just your desktop machine with one or two GPUs in there. It's really hard to keep up with a top industry or academia lab where people can have like a DGX for themselves. And I think we have to think about how we can address that in the future. Because data is becoming more and more important, but also the compute to deal with the data efficiently. I don't have a solution for it, but maybe like if a data set is open source, maybe like a Google Colab or like AWS, where you wouldn't have to download the data, but you could just like access it and train on these machines. It would have to be free, and it's a money investment for whoever does that, but like that would be a good thing, I guess.
Yeah, about sharing the other classic problem is that you don't load the data, and then you're like, whoa, now how do I load this? Why do they have one more bone than my skeleton? Why the depth map is 16-bit and not 8-bit, and all this mess, right? So standardization is also something we should work on a little bit, I think. I think deep learning in that sense helped a little bit because, yeah, sharing models and train networks and architectures is slightly more standard, but still it can take 1 or 2 or 1 week to just run a model that you don't load because there's some parameter that you don't understand or whatever. I think we do not want to overrun this. I don't know, Christian, Armin, you're more into organization stuff. should we leave it here, or do we want to do another round of questions? Maybe.
If anyone has any last comments, it would be nice, and then we can conclude.
Yeah, I see Zhong Wai.
Yeah, so for my research, the 3D face reconstruction, I encountered a problem, not a problem, just a question that I need the landmark detection method to detect the landmark first. And I think I find that using other people's algorithm and the landmark detection method usually are not very accurate for some extreme pose. So, and because my method for 3D face reconstruction is based on their method, like if they didn't detect the landmark very correctly for some images, so my reconstruction were not very accurate. And this is the one problem. So that I think method based on like supervised learning is not a way to go. Like, I wonder whether we can like develop some unsupervised learning or semi-supervised learning to make it like can use like a large amount of data even for the landmark detection. So I don't know like the way to go, like how to make it more accurately.
There was an interesting paper from the University of Washington. I forget the name of the last name of the first author was Supasorn. It was one of Steve Seitz's students. They had an interesting work about trying to automatically discover correspondences across, you know, they were not, I mean, deformable objects in the classic sense, but categories of objects. I think that's a really promising direction for sure. Yep.
Mm-hmm. All right. Do we have any last thoughts? Any of the speakers or panelists want to share? Okay, in that case, I think we can wrap up the panel discussion here. I want to thank you, everyone, for contributing to the workshop, especially the speakers. We had some technical issues at the beginning, but we managed. Actually, Yaser managed to plug in the hacking actually into the talk. That was very nice. The way you handle the the technical difficulties and put it back into your topic. That was a great way to handle it. So I think I will leave it up to either Marco or Armin, who's doing the closing session. Sorry, I forgot.
So I think Christian is doing the closing session.
Okay, so we have a last session which should last less than 5 minutes, where we announce the best paper award and some summary of the workshop, I think. Are you, Christian, ready for that? Okay. Yeah, Christian is our technician here. He's doing a great job at managing all the audio and video inputs.
Okay, I think that is a go. Right, so it's my great pleasure to announce our best paper prize at the second DynaVis workshop. And this is, as I mentioned in the opening session, is an NVIDIA Titan RTX graphics card. And we agreed to give the prize to, drumroll, Semi-supervised 3D face representation learning from unconstrained photo collections by Zhongpei Gao, Yuyong Zhang, Yudong Gu, Tao Ma, Guang Tao Zhai, and Xiaofeng Yang from the Artificial Intelligence Institute at Shanghai Jiao Tong University and the University of Science and Technology of China. So maybe we could get Zhangpei to join briefly into the chat, to the video.
Oh, thank you very much. It's very unexpected.
Congratulations from the entire organizer team. So please contact us with your postal address, and NVIDIA will send the card directly to you.
Okay, thank you very much.
Thank you, Zhangpei. And that brings me to the next, where I thank everybody else. I wanted to thank particularly our workshop attendees and everyone watching a recording for bearing with us while we try to figure out this new streaming landscape and how to handle Zoom bombing in particular. Also wanted to thank everybody who submitted their work or workshop. And I wanted to thank all our external paper reviewers who helped us review all the submissions. Particularly, I wanted to thank all the presenters today, all our paper authors, our keynote speakers, Yaser and Raquel in particular, for their time, for their interesting and insightful talks. I want to thank our sponsor, NVIDIA, for the Best Paper Prize. And finally, I want to thank my workshop co-organizers, Armin, Marco, Michael, Dan, and Adrian Hilton. And hopefully we see you next year at DynaVis, the third international workshop on dynamic scene reconstruction.